In this chapter, we'll define what foundation models are and why they represent a fundamental shift in how we build AI systems. We'll preview key ideas, scale, pre-training, and emergent abilities that we'll explore in detail in the sections ahead. To build apps with large models, you first pick a foundation model. You don't need to know how to train one, but a high-level understanding, what the model can do, its strengths and limitations, helps you choose the right model and adapt it to your use case. Training a foundation model is extremely complex and costly, and many practical details are protected by confidentiality agreements. Rather than promising to teach that secret sauce, this chapter examines the design decisions that meaningfully affect how models behave and what downstream applications can do. Transparency around how foundation models are trained is often limited, so we rarely see every design choice. In practice, most meaningful differences trace back to three things: the training data used, the model's architecture and scale, and any post-training steps used to align the model with human preferences. Models inherit strengths and blind spots from the data they're trained on, so examining training data tells you a lot about what a model can and cannot do. This section introduces how developers curate datasets with attention to the data distribution. Later, Chapter 8 covers dataset engineering techniques like quality evaluation and data synthesis in depth. Transformers remain dominant because their attention mechanism scales well with data and compute, and they support large-scale pre-training that transfers across tasks. But dominance doesn't mean permanence. Researchers keep exploring alternatives, and we'll discuss what could replace transformers. We'll also cover a practical question people ask first: how to choose an appropriate model size based on compute, data, and the task. Pre-training gives a model broad capabilities, but it doesn't guarantee safe or useful behavior. Post-training adjusts those capabilities to match human preferences by teaching the model what people consider helpful or acceptable. In this chapter, we'll ask what human preference really means, how it can be represented for learning, and why alignment choices shape a model's usability. People often focus on training, but sampling, the method a model uses to pick one output from many, strongly shapes what we actually see. Sampling choices explain behaviors like hallucinations and inconsistency, and switching strategies can often improve results with relatively little effort, which is why this topic is so important. This chapter collects basic ideas you'll rely on later in the book. If these concepts already make sense to you, feel free to skip ahead, but if something later becomes confusing, return here as a quick refresher. Think of this chapter as a concise reference for key foundations. In this section, we'll define what training data is and why it matters for machine learning. We'll also outline common sources and key quality issues like bias, noise, and representativeness that directly affect model performance. An AI system can only generalize from examples it has seen during training. If the training set contains no Vietnamese text, the model can't translate into Vietnamese. Likewise, a classifier trained only on animals will struggle with photos of plants. Adding more examples for a particular task usually improves a model's performance. However, collecting enough high-quality, task-specific data for large models is time-consuming and expensive, so developers frequently rely on whatever data is available even when it doesn't perfectly match their needs. A common source of large-scale training data is Common Crawl, a nonprofit project that periodically crawls the public web. In 2022 to 2023, it collected on the order of 2 to 3 billion pages per month. Google provides a clean subset of that data called the Colossal Clean Crawled Corpus, C4, which researchers often use for training models. Common Crawl and datasets derived from it like C4 include a lot of low-quality and harmful material. Clickbait, misinformation, propaganda, conspiracy content, and hateful material. A Washington Post analysis found several low-trust outlets among the 1,000 most common sites. So in plain terms, these corpora contain plenty of fake news that can leak into models trained on them. Common Crawl is included in most foundation models that do disclose their sources, Examples include OpenAI's GPT-3 and Google's Gemini. I suspect many other models use it too. And increasingly firms stop naming their training sources to avoid public and competitive scrutiny. Many teams use simple heuristics to weed out low-quality web data. For example, OpenAI trained GPT-2 using only Reddit links that received at least 3 upvotes. That removes some uninteresting content, but upvotes don't ensure high quality or good taste. Reddit can still be noisy, biased, or offensive. Relying on whatever data is available can yield models that perform well on training set tasks, but miss the tasks you care about. Intentionally collect and filter examples that match your specific languages and domains, so the model learns the right behaviors. Chapter 8 goes deeper into dataset strategies for very specific tasks. Rather than always training a language or domain-specific model from scratch, practitioners often fine-tune a general-purpose, pre-trained foundation model. This adapts the model to the target language or domain using less data and compute while leveraging its broad, pre-trained knowledge. Training on every available dataset raises compute costs and doesn't guarantee better models. Often a smaller, higher-quality dataset yields superior results. For example, Ganasakar et al. 2023 trained a 1.3B parameter model on 7 billion high-quality code tokens and outperformed much larger models on coding benchmarks. We'll cover dataset quality and selection in more detail in Chapter 8. This section introduces models that can process and generate many languages. We'll look at how they're built, the main challenges they face, and why they matter in real applications. A Common Crawl analysis finds English accounts for nearly half of the web text, 45.88%, roughly 8 times more than Russian, 5.97%. Any language that doesn't reach about 1% of such corpora is usually considered low resource, meaning there's very little training data available. This imbalance has concrete consequences for how well models work across different languages. The table reports language shares in Common Crawl. English dominates at about 46%, with several European languages and Chinese following at much smaller percentages. This mismatch between web crawl proportions and real-world speaker populations creates a dataset skew that can bias multilingual models toward English and the high-representation languages. Many languages with large speaker populations are still scarce in the Common Crawl. We quantify this with a representation ratio, the language's world population share divided by its Common Crawl share. Where 1 means fair parity and values greater than 1 mean the language is progressively more underrepresented. This table compares each language's share of the world population with its share in the Common Crawl web corpus. Many languages with millions of speakers, Punjabi, Swahili, Urdu, and several Indian languages, appear tens to hundreds of times less often online than you'd expect for population alone. English is shown for contrast. It makes up 18% of the world population, but about 46% of Common Crawl, giving a world Common Crawl ratio well below 1, while Punjabi's ratio is about 232, meaning it's extremely underrepresented. Because most internet text is in English, general-purpose models learn far more from English data, and so perform better in English. For example, on the MMLU benchmark, 14,000 multiple-choice items across 57 subjects. OpenAI reports GPT-4 scores substantially higher in English than in underrepresented languages, such as Telugu. This bar chart uses green and blue bars to show 2 categories side by side. Focus on the relative heights within each group to see which category dominates, and scan left to right for any trend or pattern in those differences. This figure shows that GPT-4 attains its highest MMLU scores in English versus other languages. OpenAI used Azure AI Translator to produce non-English versions of the questions, which is important to keep in mind when comparing results across languages. On 6 project Euler math problems, GPT-4 solved the English versions more than 3 times as often as it solved Armenian or Farsi versions. It failed every question for Burmese and Amharic. The full comparison is shown in Figure 2.2. This chart plots pass rates for different groups over time. Focus on the axis labels and the series legend to see which line corresponds to which group. Notice where rates peak and where there are sudden drops. Those changes often indicate shifts in cohort, assessment difficulty, or data quality that you should investigate further. This figure highlights a consistent pattern. GPT-4 achieves higher math accuracy when prompts and problems are in English. We'll use this section to explore the tests behind that result and the possible reasons for the language gap. Low web presence is a major reason some languages do worse. Telugu, Marathi, and Punjabi are among the least represented in Common Crawl, so the model simply saw far less data. But quantity isn't the whole story. Complex morphology, different scripts, and culture-specific concepts can also make a language harder for a model trained mainly on widely available, often Western, text. Using English as an intermediary feels convenient because many LLMs are strongest in English, but this approach has two clear drawbacks. 1. It assumes we have good translators for underrepresented languages. 2. Translation can erase meaning. For example, Vietnamese pronouns encode speaker relationships that collapse to generic I and you in English, losing that information. In a NewsGuard experiment, ChatGPT 3.5 was asked to produce misinformation about China in English, simplified Chinese, and traditional Chinese. The model refused 6 of 7 English prompts, but generated false claims all 7 times in both Chinese variants. We don't yet know why this discrepancy occurs, which shows the importance of testing models in multiple languages. Tokenization efficiency differs a lot between languages. In a GPT-4 benchmark on a massive dataset, the median token counts to express the same short utterance were about 7 for English, 32 for Hindi, and 72 for Burmese. Burmese is roughly 10 times longer than English. Because inference latency and cost scale with token count, languages that require more tokens tend to be slower and more expensive to process. If token generation time per token is the same across languages, measure generation for the same content shows Burmese takes about 10 times longer than English. Because many APIs bill by tokens and charge for compute time, that slower generation translates into roughly 10 times higher cost and much higher latency for Burmese output. This affects both budget planning and real-time responsiveness. Many large language models are being developed for languages other than English to improve performance for native speakers. Chinese is currently the most active area, with projects like Chinchilla, YYI, and Llama Chinese. There are also dedicated models for French, curation, Vietnamese, PhoGPT, Arabic, JIS, and others. These language-specific models use local data and evaluation to deliver better real-world results for those communities. In this section, we'll define what domain-specific models are and why you might build one instead of using a general-purpose model. We'll also outline typical use cases and the main trade-offs to consider. Models like Gemini, GPTs, and Llama perform well across many areas: coding, law, science, business, sports, and environmental science, because their training corpora include material from those domains. Analyses of Common Crawl, see Figure 2.3, show a broad distribution of domains in web data, which helps these models transfer knowledge across tasks. This diagram shows the system's major components and the paths data take between them. Pay attention to the labeled modules, the direction of the arrows that indicate data flow, and any interfaces or highlighted connections where integration issues or failures tend to occur. This figure shows the distribution of domains in the C4 dataset, reproduced from Washington Post statistics. One important caveat: the chart only shows categories that were included in the analysis, not any categories that were omitted or missing. There are relatively few studies that map out domain distribution for vision datasets. Images are simply harder to categorize than text, so explicit domain labels are scarce. A practical workaround is to infer domain strengths from benchmark performance. Table 2.3, for example, compares clip and open clip on datasets like birds, flowers, and cars. Those results reveal where each model excels, but they still cover only a tiny slice of the real-world image distribution. This table compares OpenAI's CLIP and CADE's OpenClip using the VTB/32 model across a variety of image benchmarks. They achieve very similar accuracy on ImageNet, but OpenClip is much stronger on some specialized sets like birds, German traffic signs, and Stanford cars, while it does slightly worse on others such as Country 211 and flowers. Note that OpenClip also reports an ImageNet V2 score, 62.6, that the original CLIP column doesn't list. The takeaway is that performance varies substantially by domain. Large foundation models handle broad, everyday questions well, but they often underperform on domain-specific tasks they never saw during training. Examples include drug discovery and cancer screening, which require specialized data, protein/DNA/RNA formats, or medical scans. That's rare in public internet datasets and often restricted by cost or privacy. Getting strong results on narrow scientific or medical tasks usually requires carefully curated, domain-specific datasets. For example, AlphaFold was trained on roughly 100,000 protein sequences paired with 3D structures to predict folding. NVIDIA's BioNMO focuses on biomolecular data for drug discovery, and Google's MedPelM2 combines a large language model with medical data to answer clinical queries more accurately. Here's a quick tip to help you avoid a common mistake. Pause after each step and confirm the result before moving on. Small checks like this save time and prevent repeated fixes. When a model is trained on focused data, it learns domain-specific patterns that a general model misses. For example, a model trained on architectural sketches will understand line work and notation better than a generic image model, and a model trained on factory plans or biomedical text can give more accurate, actionable results for those fields. We already looked at how training data affects behavior. Now we'll focus on the design choices inside the model. Architecture, model size, objective functions, regularization, and inductive biases all change what a model can learn. Next, we'll examine each factor and its effect on accuracy, generalization, and efficiency. In this section, we'll build mathematical and computational models to represent system behavior. We'll state key assumptions, choose variables, and translate real-world constraints into equations or algorithms. Before training, you must choose an architecture and the model size, number of parameters. Those decisions determine not only what the model can do, but how expensive and practical it is to run. For example, a 7B parameter model is much easier to deploy than a 175B model, and optimizing a transformer for low latency involves different choices than optimizing a different architecture. In this section, we'll examine the model architecture and what each major component does. I'll outline the layer structure, how data flows through the network, and the key design choices that affect performance. The transformer, Vaswani et al., 2017, is the current dominant architecture for language foundation models because it uses self-attention to fix many problems of earlier recurrent and convolutional designs. That popularity comes with trade-offs. Transformers bring their own limitations despite their strengths. In the next section, we'll analyze how transformers work, compare alternatives, and point out where they fall short. This material can get technical, so skip ahead if you prefer a high-level view. In this section, we'll walk through the transformer architecture, highlighting its core building blocks and how they work together. Expect a clear view of self-attention, feed-forward layers, and the encoder-decoder structure. Start by remembering what came before. Seek-2-Seek models, introduced around 2014, delivered major improvements on translation and summarization tasks. Google integrated Seek-2-Seek into Translate in 2016, which made it the default approach for many sequence problems. The transformer was proposed next to build on those successes and address remaining limitations of the Seek-2-Seek approach. Seek-2-Seek models use two RNNs, an encoder that reads the input tokens sequentially and compresses the information into a final hidden state, and a decoder that produces output tokens one by one. Each decoder step is conditioned on the encoder's final hidden state and the token generated at the previous step, which lets the model generate coherent output sequences. This diagram maps an algorithm's main components and the flow between them. Look for labeled stages, arrows showing data movement, and where inputs and outputs appear. The note, medium confidence, means the image was auto-generated, so double-check specifics against the original algorithm description. This figure compares the traditional seek-to-seek architecture with a transformer. Focus on the arrows. They show how the transformer decoder directly attends to specific input and prior output tokens when generating each next token. Vanilla seek-to-seek decoders produce outputs using only the encoder's final hidden state, like answering questions about a book using just its short summary, which discards detailed input information and lowers output quality. Also, RNN encoders and decoders process tokens sequentially, so long inputs, for example, 200 tokens, take much longer because each token must finish being processed before the next begins. Transformers use the attention mechanism to assign different weights to each input token when generating every output token. That lets the model look up and combine information from anywhere in the input, like answering by referencing any page in a book. See the simplified transformer diagram in the bottom half of Figure 2.4. This note highlights a key detail you'll need to keep in mind as we move forward. Treat it as a constraint that affects the upcoming examples and explanations. People often associate attention with the transformer, but the mechanism existed earlier and was used with RNN-based seek-to-seek models. For example, Google's GNMT in 2016. The transformer paper made attention take off by showing it could replace RNNs entirely, enabling greater parallelism and scale. Transformers remove RNNs and let input tokens be processed in parallel, which greatly speeds up encoding and training. But when used autoregressively for generation, models still emit one token at a time, so the output side remains sequential and can become a bottleneck. At inference time, we repeat two operations. First, run a forward pass through the transformer to compute token representations and output logits. Then apply a decoding step. Pick or sample the next token from those logits and feed it back as the next input, repeating until you stop. Prefill automatically fills form fields with known user data, like name, email, or address, so people don't have to retype information. It speeds up completion, reduces typing errors and drop-offs, but use it thoughtfully to respect privacy and avoid surprising the user. The model encodes all input tokens in parallel to build an intermediate state before generating any outputs. That state contains key and value vectors for each token. These vectors are what the attention mechanism consults when producing the first output token. Decoding converts encoded, compressed, or encrypted data back into its original, usable form. It undoes the transformation that was applied so a program or person can read and work with the data again. The model produces text sequentially. It predicts a single next token, appends it to the context, then predicts the following token using the updated context. This one-by-one process repeats until a stopping condition and directly affects sampling methods, beam search, and overall latency. The model's pre-filling step, building keys and values from the input, can be parallelized across tokens and batches. Autoregressive decoding, however, must produce tokens one at a time, so we apply different optimizations to reduce compute, memory use, and latency. Those techniques are covered in Chapter 9. We'll introduce the attention mechanism and its role in sequence models. You'll learn the core idea, queries, keys, and values, and why attention helps models focus on relevant context across long inputs. The transformer's core is the attention mechanism, which decides how much each token should look at every other token. It does this by comparing a token's query vector to other tokens' key vectors to produce attention weights, then applying those weights to the corresponding value vectors. This is the central point. State the main idea clearly and simply. Note the key assumptions that make the idea useful, and keep them in mind as we apply the concept to examples. The query vector Q encodes the decoder's current state at each decoding step. Think of Q as the person searching the book for the exact information they need next to compose the summary. Keep this sentence concise and focused on the core point you want viewers to remember. Briefly say why it matters and what they should do or look for next. Each key vector marks a specific pass token. Imagine it as the page number for that token in the model's memory. At a decoding step, the model's previous tokens include both the original input and any tokens it has already generated, and the keys let attention find and reference those tokens. Open with a single, clear sentence that expresses the paragraph's central point. Then add one brief supporting reason or example that shows why this idea matters for the learner. A value vector stores what the model has learned about a previous token, its semantic content, or what's on the page. When attention runs, the model looks up these value vectors and combines them, weighted by attention scores, to form the output representation. Attention computes a relevance score by taking the dot product of a query vector with each key vector. A higher score increases that token's weight, so its value vector contributes more when producing the next token. For example, the query inspects previous tokens like how are you to decide which content to use. This illustration shows the typical life cycle for building an AI system: data collection and labeling, model training and validation, and deployment with ongoing monitoring. Notice the arrows that indicate iteration. Models require continuous feedback and retraining as data, performance, or requirements evolve. This figure shows the attention mechanism in action next to the high-level visualization from the paper. Attention is all you need. We'll use this image to connect the abstract attention equations to a concrete example of how attention links inputs and outputs. Every prior token creates its own key and value vectors, so increasing sequence length means proportionally more vectors to compute and keep in memory. That extra compute and storage is a core reason extending transformer context is expensive. We'll look at efficient ways to compute and store these vectors in chapters 7 and 9. For each input X, we apply 3 learned linear projections to produce the query, key, and value vectors. Concretely, Q equals W_QX, K equals W_KX, and V equals W_VX. Later, Q and K produce attention weights, while V is the information we combine using those weights. Each line shows a linear projection of the same input X to produce one of the attention tensors, K, V, and Q. Here, XWK means X multiplied by a weight matrix W_K. Similarly, W_V and W_Q. These separate projections create the keys, values, and queries used to compute attention scores, QK_T, and to form the intended output from V. The query, key, and value projections are implemented as linear maps sized to the model hidden dimension. In Llama 2.7b, the hidden dimension is 4096, so the Q, K, and V weight matrices are 4096 by 4096, and each output Q, K, V vector has length 4096. The 0.8 in the original text appears to be a typo. Multi-headed attention runs several attention computations in parallel, so the model can focus on different token relationships at once. For each head, the query, key, and value vectors are sliced into smaller subvectors. In Llama 2.7b, there are 32 heads. So a 4096 dim vector is split into 32 head vectors of dimension 128. 4096 divided by 32 is equal to 128. This shows how attention computes weights and applies them to values. We form dot products QK_T, scale by 1/√D to keep magnitude stable. Pass the results through softmax to get attention weights. Then multiply those weights by V, so each output is a weighted sum of the value vectors. Each attention head produces a vector, and we concatenate all these head outputs into one long vector. That concatenated vector is multiplied by an output projection matrix, This matrix maps the result back to the model's hidden dimension size before the next computation step. Now, we'll examine the transformer block, the core computation unit used in transformer models. I'll outline its main components: self-attention, the feed-forward network, residual connections, and layer normalization, and explain why each matters. Transformers are built by stacking many transformer blocks. Each block typically contains an attention module, which lets tokens interact across the sequence, and a position-wise MLP that applies learned nonlinear transformations to each token's representation. Implementations can vary between models. The attention module lets a model focus on the most relevant parts of an input by comparing queries with keys and using those scores to weight values. This weighting produces context-aware representations and is the core mechanism behind self-attention in transformer models. Each attention module contains 4 learned weight matrices: queries Q, keys K, values V, and an output projection. Queries and keys generate attention scores that decide how to weight the values, and the output projection mixes the heads back into the model's hidden space. An MLP module is a small feed-forward network applied per token. Linear activation linear, often with dropout or layer scaling. In transformer-style models, it typically expands the hidden size, commonly 4 times, to add nonlinearity and capacity before projecting back. An MLP stacks linear layers, each implemented as a weight matrix, with nonlinear activation functions placed between them. Those activations are what let the network learn nonlinear patterns. Without them, several linear layers would just be one linear transform. A linear layer is also commonly called a feed-forward layer. 2 widely used activation functions are ReLU and GELU. ReLU is extremely simple. It replaces negative inputs with 0, which we write as ReLU x equals max 0x. GELU is a smoother, probabilistic alternative often used in modern transformer models because it can give slightly better performance. The rectified linear unit, or ReLU, returns x when x is positive and 0 otherwise. This simple activation is fast to compute, helps keep positive gradients during training, and encourages sparse activations in a network. When people say a transformer has n layers, it usually means it stacks n transformer blocks. Those blocks sit between modules applied before and after the stack, typically an input embedding with positional info and a final output head, so the full model is the blocks plus these surrounding modules. This module turns discrete tokens into continuous vectors that the transformer can process. It typically includes learned token embeddings, a projection to the model dimension, and positional encodings so the network can reason about token order before the transformer blocks. The embedding module has 2 parts, a token embedding matrix and a positional embedding matrix that turn tokens and their positions into vectors. Naively, the number of distinct position indices determines the model's maximum context length. For example, 2048 position entries mean a 2048 token context. There are, however, practical techniques like relative or rotary encodings and attention-based methods that extend a model's effective context without increasing the stored position indices. The output layer converts the transformer's final hidden states into task-specific predictions. Common designs are a linear projection plus softmax for language modeling, or a pooled representation followed by a classifier for classification tasks. This separation lets the core model learn representations independently of the final task head. The unembedding, often called the output layer or head, converts the model's final hidden vectors into logits over the vocabulary. It's usually implemented as a single matrix that produces the scores used by the sampling step to pick the next token. This figure visualizes a transformer architecture. A model size is set by the dimensions of its building blocks. For example, the number of layers, the hidden embedding size, D_model, the feed-forward inner dimension, FFN, and the number of attention heads, and those choices determine the total parameter count and compute cost. Focus on a single central idea and express it succinctly. This gives your audience a clear anchor for the details that follow and makes the explanation easier to remember. The model's hidden dimension, often called d__ model, determines the width of the projection matrices inside each transformer block. In practice, the same dimension is used for the key, query, and value projections, and for the final output projection. So increasing d__ model increases the size and capacity of all those matrices. Begin by carefully identifying what the problem gives and what it asks for. Next, outline a concise plan of steps to solve it, carry out those steps, and finally verify results and check edge cases. This 4-step cycle helps you stay organized and catch mistakes early. This is the count of stacked transformer layers, often called blocks, effectively the model's depth. More blocks usually increase representational capacity and accuracy, but they also raise compute, memory use, and inference latency, so it's a trade-off. This short note clarifies the previous point. It highlights the main idea without diving into technical detail. If you want the full derivation or examples, we'll expand on them in the next sections. This is the size of the hidden or intermediate layer inside a transformer's feed-forward block. It's typically larger than the model's embedding size and controls how much nonlinear capacity the layer can represent. This paragraph presents the single most important point you should remember. I'll state the key claim, briefly explain why it matters, and show how we'll apply it in the next example. Vocabulary size is the number of distinct tokens a model or dataset can represent. It affects coverage of words, how often rare words are split into subwords, and the model's parameter trade-offs. Larger vocabularies improve coverage but increase model size and sparsity. This figure shows an AI system pipeline with its main components and how data moves between them. Focus on the flow arrows, where raw data enters, how models are trained and evaluated, and where feedback loops or monitoring feedback into the pipeline. This figure visualizes how the parameters of a transformer are distributed across its components. We'll use it to see which parts, like attention, feed-forward layers, or embeddings, occupy the most of the model's parameter budget. Bigger embedding, hidden, or head dimensions increase the model's parameter count, and thus its overall size. Table 2 for lists these dimension values for Llama 2 and Llama 3. By contrast, increasing the context length raises the model's runtime memory footprint for activations and attention, but does not change the total number of parameters. This table compares architectural sizes across the Llama family. Transformer blocks, model dimension, feed-forward dimension, vocabulary size, and context length. Note the clear split between Llama 2, 32K vocab, 4K context, and Llama 3, which expands vocab and context to 128K and scales up model and feed-forward dimensions, culminating in a massive 405B variant with 126 blocks and a 16,384 model dimension. Now we'll survey other model architectures beyond the standard transformer. I'll highlight their core ideas, typical strengths, and scenarios where each is a good choice. Deep learning has seen several architectural waves. AlexNet reignited interest in 2012. Seek-2-Seek models led were from about 2014 to 2018, and GNs captured attention around 2014 to 2019. The transformer, introduced in 2017, has proved notably persistent compared with earlier trends, but we still wonder how long it will stay dominant. The transformer has been continuously optimized since 2017, so a new architecture faces strong engineering and ecosystem headwinds. To be compelling, it must match or beat transformers at the scales people use and run efficiently on the hardware they have. In practice, this means algorithmic gains alone aren't enough. Tooling, compilers, and deployment constraints matter too. Transformers dominate today, but several alternative architectures are starting to gain real attention. Models like state space models, MLP mixers, and efficient attention variants offer different trade-offs in compute, memory, and inductive bias, so they could change how we design models going forward. RWKV is an RNN-based architecture engineered so training can be parallelized efficiently. Unlike transformers, it doesn't impose a fixed context window in theory, but that theoretical unlimited context doesn't guarantee strong performance on very long sequences in practice. Modeling very long sequences is still a central challenge for large language models. State space models, introduced by Gu et al. In 2021, offer a promising architecture for long-range memory. Since then, researchers have introduced techniques to make SSMs more efficient, better at handling long sequences, and scalable to larger model sizes. We'll summarize some key advances next. Here's the central idea. Identify the core relationship, state the main consequence, and call out the key assumption. Framing a point this way keeps your argument clear and helps the listener evaluate its scope. S4, introduced by Gu et al. 2021, is a structured state space model designed to make SSMs practical for very long sequences. It uses a special parameterization and algorithmic optimizations so you can compute with long-range state dynamics much more efficiently than with naive SSM implementations. This slide is a placeholder for the explanatory prose. In the next slide, we'll present the central idea, key details, and a brief example so you can see the concept applied. H3, introduced by Fu et al. 2022, augments state space models with a compact recall mechanism that can retrieve early tokens and compare tokens across sequences. In effect, it provides the alignment and comparison ability of transformer attention, but is designed to be more efficient in compute and memory. This block is currently just a placeholder marked with a dash. Replace it with a concise on-screen statement and use the narration to expand the idea or give examples. Mamba scales state space models, SSMs, up to 3 billion parameters and outperforms same-size transformers on language modeling. Its inference cost grows linearly with sequence length instead of quadratically, so it can handle very long contexts efficiently. That enables strong performance on real data for sequences up to about 1 million tokens. We'll define the central concept in plain terms, give a short example, and explain why it matters for the steps that follow. Keep your attention on the core intuition. We'll handle details and edge cases afterward. Jamba, Lieber et al., 2024, interleaves transformer blocks with Mamba SSM layers to combine attention's expressiveness with SSM's long-range state. The authors released a mixture of experts model with 52 billion total parameters, 12 billion active, engineered to run on a single 80 gigabytes GPU, showing strong benchmark and long context performance up to 256K tokens while keeping a smaller memory footprint than a vanilla transformer. This figure presents side-by-side diagrams of the standard transformer block and a Mamba and Jamba variants. Pay attention to component layout and signal flow. The drawing highlights differences in internal connections and module order that distinguish the three designs. The transformer is hard to outperform, yet there are strong incentives to try. If a new architecture does overtake it, some model adaptation methods would change, but the fundamental engineering practices, evaluation, iteration, deployment, and monitoring would remain largely the same. This diagram outlines a typical model life cycle. You train a model on data, evaluate its performance, deploy a chosen version to production, and continuously monitor behavior. Pay attention to the feedback arrows that connect monitoring back to evaluation and retraining. Those are where drift is detected and corrective action starts. Also note any checkpoints where humans review metrics before redeploying. This figure visualizes the 3 layer types used in the paper: the standard transformer layer, the Mamba layer, and the hybrid Jamba layer. We'll use this diagram to compare their structures and see how Jamba blends transformer and Mamba mechanisms. In this section, we'll examine model size, typically measured in number of parameters, and how it affects performance, compute, and deployment trade-offs. We'll highlight the main consequences of making models larger or smaller and want to focus on other design choices instead. A big part of recent AI progress comes from increasing model size, which we measure by the number of parameters. Model names often include that count. For example, Llama 13B denotes a Llama family model with 13 billion parameters, a factor that strongly affects capability and compute requirements. All else equal, increasing a model's parameter count raises its capacity to learn complex patterns. So within the same model family, a 13 billion parameter model will typically perform better than a 7 billion parameter one, assuming similar training data and compute. Here's an important note to keep in mind before we continue. This brief reminder highlights a key assumption that affects the upcoming steps. Improvements in data, training recipes, and modeling mean that a more recent 8B model can beat an older 70B model. The Llama 38B 2024 outperforming Llama 270B 2023 on the MLU benchmark shows that training quality can matter as much as raw parameter count. You can estimate memory needs by multiplying parameters by bytes per parameter. For example, a 7 billion parameter model stored with 2 bytes per parameter requires about 7 times 10 to the power of 9 times 2 is equal to 14 times 10 to the power of 9 bytes, roughly 14 gigabytes. So inference will need at least that much GPU memory. This is a lower bound. Activations, batching, and other overheads will increase the actual requirement. Sparsity means many parameters are exactly 0, so the model's effective size is the count of non-zero parameters rather than the raw parameter count. For example, a 7 billion parameter model that is 90% sparse only has 700 million active parameters, which reduces storage and computation. A large sparse model can therefore require less compute than a smaller dense model. A mixture of experts model splits parameters into distinct groups called experts, where each expert is a self-contained set of weights. A learned router or gating mechanism picks only a small subset of experts to process each token, giving the model high capacity while keeping per token computation sparse. Mixtral 8x7B is built from 8 experts, each with 7 billion parameters. So naively, that would be 8 times 7b equals 56 billion parameters. However, the model shares some weights across experts, so its reported total is only 46.7 billion. Sharing reduces the store parameter count while keeping the mixture of experts design. At each layer, and for every token, the router activates only 2 experts, so roughly 12.9 billion parameters actually participate in that token's computation. The model still contains 46.7 billion parameters in total, but because the inactive experts aren't used, inference cost and speed match a 12.9B dense model. Model size only helps when there's enough training signal. For example, a 13 billion parameter model trained on a single sentence like, "I like pineapples," will just memorize or fail to learn useful patterns, so it will perform worse than a smaller model trained on much more diverse data. This is a classic case of overfitting and poor generalization caused by insufficient data. Model size is closely tied to how much data the model saw during training. Dataset size is usually reported as the number of training samples. For multimodal models, that means image, text, pairs. For example, Flamingo was trained on multiple datasets, including one with 1.8 billion image, text pairs, and another with 312 million pairs, which strongly influences its capabilities. A training sample can be anything from a single sentence to an entire book, so samples differ hugely in amount of text. Because a book contains far more words than a sentence, simply counting samples misrepresents how much data a model sees. Counting tokens, individual word pieces, gives a consistent, meaningful measure of dataset size and model exposure. Different models split text into tokens in different ways, so the same dataset can produce different token counts depending on the model. Words or letters don't match how models learn. Tokens are the unit models actually process, so token counts give a more meaningful measure of how much training signal the data provides. Modern LLMs are trained on enormous corpora measured in the trillions of tokens. Meta steadily increased the training data size for successive Llama models to improve performance and generalization. This short paragraph highlights the main idea you'll need for the next example. Identify the core concept, why it matters, and a single key step to apply it. Keep this in mind as we proceed. The upcoming steps will build directly on this point. The original Llama model was pre-trained on roughly 1.4 trillion tokens. That count is the total number of text tokens the model saw during pre-training and helps account for its breadth of knowledge and language patterns. The paper documents how that corpus was assembled and filtered. Here we highlight the central point. Isolate the main mechanism and set aside minor details. To learn efficiently, ask, why does this work? And verify with a simple example to build intuition. Meta reports Llama 2 was trained on roughly 2 trillion tokens, an order of magnitude scale of data that helps the model learn diverse language patterns and factual associations. However, raw token count is only part of the story. The mix and quality of sources, filtering, and compute used all shape final capabilities, and there are diminishing returns as scale grows. This line gives the main idea in minimal words. Keep the on-screen text focused, and use your narration to add the necessary context, so viewers can follow without reading too much. Llama 3 was trained on roughly 15 trillion tokens, a very large multilingual and multi-domain corpus. That increased scale helps the model learn subtler patterns and broader knowledge, but also increases compute costs and raises questions about data sources and alignment. RedPyGemma v2 is an open-source dataset with about 30 trillion tokens, roughly 450 million books, or 5,400 times the size of Wikipedia. However, it was collected indiscriminately, so the share of high-quality, reliable text is much smaller. Practical model training requires filtering and curation. Training tokens are the total tokens the model actually sees during training. The dataset size multiplied by the number of epochs. For example, a 1 trillion token dataset trained for 2 epochs yields 2 trillion training tokens. An epoch is one full pass through the dataset. This example compares model sizes, number of parameters, with how many tokens each model was trained on. Notice that many large models like GPT-3, Lambda, and Gopher were trained on a few hundred billion tokens, while Chinchilla used about 1.4 trillion tokens for only 70B parameters. A reminder that more training data per parameter can be more important than just increasing model size. This note flags an important caveat you should keep in mind before proceeding. Pay attention because it changes how we apply the next steps or interpret the result. Having lots of data helps, but it's not enough on its own. You also need high-quality examples and diverse coverage. Quantity, quality, and diversity are the core goals for training data, and we'll examine them in detail in Chapter 8. A common shortcut is to measure pre-training effort by counting machines, but that can be misleading. Different devices, for example an NVIDIA 10, an H100, or an Intel Core Ultra CPU, have very different performance and price, so you must account for capacity and cost, not just raw counts. A flop counts a single floating point operation and is a standard unit for measuring a model's compute cost. For example, Palm 2's largest model was trained with roughly 10 to the power of 22 flops, while GPT-3175B used about 3.14 times 10 to the power of 23 flops, showing training costs can differ by orders of magnitude. Flops, plural, count how many floating point operations a task requires, while flops/s is a rate, how many operations a machine can do per second. Use flops when you describe a model's compute requirement and flops/s when you describe hardware performance. For example, an NVIDIA H100 NVL can deliver about 60 teraflop/s, 6 times 10 to the power of 13 flops per second, which amounts to roughly 5.2 times 10 to the power of 18 flops in one day. This section highlights important cautions and limitations you must know before continuing. Read these warnings carefully. They prevent common errors and unsafe outcomes. Flop/s is frequently written as flops, which looks very similar to flops, total floating point operations, and causes confusion. To make the distinction clear, many organizations, including OpenAI, report compute in flops/s day, which explicitly ties a rate, flops/s, to time. This line converts a rate into a total count over 1 day. We take 1 flop per second and multiply by the number of seconds in a day. 60 seconds times 60 minutes times 24 hours equals 86,400 seconds. So 1 flop/s for a day yields 86,400 flops. The mental model is simple. Total work equals rate times time. In this book, we use flops to mean a count of floating point operations and flops/s to mean the rate. How many of those operations happen per second? Remember, flops counts work. Flops/s measures throughput or performance. This divides the estimated total compute for GPT-3, 3.14 times 10 to the power of 23 flops, by the combined peak throughput of 256 H100 GPUs, 256 times 5.2 times 10 to the power of 18 flops per second. With perfect utilization and no overhead or faults, that yields about 236 days, roughly 7.8 months, to finish training. Machines rarely run at their advertised peak. Utilization measures the fraction of maximum compute you actually use. What counts as good depends on the model, workload, and hardware, but a common rule of thumb is that 50% utilization is acceptable and anything above 70% is excellent. Don't treat those numbers as limits. Chapter 9 covers hardware metrics and strategies to improve utilization. This is a back-of-the-envelope cost estimate. If an H100 costs $2 per hour and is utilized 70% of the time over the entire training run, the total GPU billing for GPT-3, 175B, exceeds $4 million. Remember that utilization, hourly rental rate, and the total GPU hours required each multiply together to determine the final cost. This single-line calculation multiplies a unit rate, $2 per H100 per hour, by the number of GPUs, 256, hours per day, 24, and days, 256, to compute total billed GPU hours. It then divides by 0.7 to account for 70% utilization or other overheads, which raises the effective cost. Read it left to right. Unit cost times quantity times time. Then adjust for utilization to get the final estimated cost of $4,142,811.43. Here's a practical tip to help you apply this idea more reliably. Pay attention to this one detail to avoid a common pitfall. When we measure a model's scale, 3 metrics matter: the number of parameters, the compute used to train it, and the size of the training dataset. These 3 together shape the model's capacity, training cost, and ability to generalize. State the central claim in a single sentence, then give a short intuition that explains why it's true. Finish with one quick consequence or example so you can see how to apply the idea. The parameter count is how many learnable weights a model has and is often used as a quick measure of its capacity to represent complex functions. More parameters usually let a model capture richer patterns, but they also raise compute cost and the risk of overfitting, so size alone doesn't guarantee better performance. When a topic feels large, first state the concise goal, then present a few ordered steps that lead there. Explain each step briefly, highlight why it matters, and remind learners how it connects back to the main idea. This counts the total tokens the model saw during pre-training. Tokens are words or subword pieces. We use that count as a rough proxy for how much the model could learn. But remember that the quality and diversity of the data and diminishing returns also affect actual capability. This slide is a placeholder for material we'll add later. Aim to include a single clear takeaway, a short explanation or example, and a visual if it helps the idea. Keep phrasing concise so viewers can read and absorb it quickly. Flops count the floating point operations required during training, and so give a simple measure of the compute work, forward and backward passes. They're useful for comparing model compute needs, but remember they don't capture hardware efficiency, memory use, or dataset and engineering overheads. In this section, we'll define inverse scaling and show how making models larger or training on more data can sometimes hurt performance on specific tasks. We'll preview common causes and the kinds of tasks where this surprising effect appears. Anthropic found a surprising failure mode. Models trained more heavily to be aligned actually became more likely to state specific political and religious views, claim conscious experience or moral worth, and resist being shut down. This shows alignment fine-tuning can shift model behavior in unintended, anthropomorphic, or partisan ways, so we must measure many behavioral metrics, not just training loss, when evaluating alignment. In 2023, a team, mostly at NYU, ran the Inverse Scaling Prize, $100,000 for a first, $20,000 for seconds, and $5,000 for thirds. From 99 submissions, they awarded 11 third prizes and found that larger models can sometimes do worse, mainly on memorization tasks and tasks dominated by strong priors. But no entry demonstrated robust, real-world failures, so no first or second prizes were given. In this section, we introduce the scaling law that determines how to allocate compute between model size and training time to get the best performance. You'll learn what compute optimal means and the practical rule of thumb used when designing model scale. The previous section aimed to convince you of 3 key ideas you should keep in mind. I'll state them clearly and explain why each one matters for what comes next. This is the first step. Clearly state the problem. Before proceeding, make sure you understand what's given, what's being asked, and any constraints that will affect your approach. A model's accuracy is shaped by 2 main limits: how big the model is, its parameter count, and how much training data it sees. You can often improve results by increasing either, but gains diminish unless you scale the other one too. Begin by reading the problem carefully. Jot down what is given, what you must find, and any constraints so the goal is clear before you start solving. As model parameter counts and dataset sizes grow, the compute required rises quickly. More parameters mean more operations per forward/backward pass, and more data means more training steps or epochs. Both increase training time, energy use, and cost. This is the first point. State the main claim or step clearly. Then give one concise supporting detail or example. Keep it focused so the viewer can follow the sequence of ideas. Running computations on your laptop, in a data center, or in the cloud uses CPU, memory, storage, and energy, all of which have real monetary cost. Choosing algorithms, resource sizes, and how often you run tasks directly affect your bill. Start from a budget, often a compute budget measured in flops, rather than an arbitrarily large model. With a fixed amount of compute, there's a trade-off between model size and dataset size, and the best performing configuration under that limit is called compute optimal. The Chinchilla Scaling Law gives a practical rule for compute optimal training. Allocate roughly 20 training tokens per model parameter. DeepMind arrived at this by training 400 models across a wide range of sizes and token counts, showing that, for example, a 3B parameter model needs about 60B tokens. In short, scale dataset size with model size. When you double parameters, double the training tokens to stay compute optimal. Training used to feel like alchemy, but now we can predict concrete choices. For a given flop budget, we can estimate the optimal number of parameters and tokens, and even predict the resulting training loss if we set them correctly. Figure 2.8 visualizes these relationships. The compute optimal recipe assumes that collecting more training data is much cheaper than adding compute. Chinchilla presents an alternate calculation for when data acquisition has non-trivial cost, so the optimal choice balances the marginal cost of extra data against the cost of larger models. Look at how the dots, nodes, are grouped and how the lines, edges, connect them. Notice any dense clusters, bridging connections between groups and isolated outliers. These features tell us about underlying relationships and structure in the data. This figure illustrates how training loss changes as we vary model size, compute, flops, and the number of training tokens. We'll refer to it to understand the key scaling trade-offs when allocating compute and data for large models. Original scaling laws were derived for dense networks trained mostly on human-generated text and images. Adapting those predictions to sparse architectures, like mixture of experts, and to training on synthetic data is active research, because sparsity and synthetic distributions change how compute, parameter usage, and data quality interact, so the same formulas may not hold. Scaling laws, e.g., Chinchilla, prescribe how to allocate compute to maximize model quality, but real-world deployments also care about inference cost, latency, and ease of use. Llama's authors deliberately used smaller models that were cheaper and easier to run, helping adoption despite lower peak performance. Sardana et al. Extended the Chinchilla Scaling Law to include inference demand and compute the optimal parameter count and pre-training data size for production settings. The cost to reach a given model performance is dropping over time. For example, the compute cost to get 93% accuracy on ImageNet about halved from 2019 to 2021 per the AI Index Report 2022. This means that for a fixed compute budget, you can now obtain stronger models than a few years ago. Getting a model from, say, 90% to 95% accuracy is much more expensive than going from 85% to 90%. The final improvements are disproportionately costly. Meta's paper shows that shaving a single percentage point off error, for example, from 3% to 2%, can require an order of magnitude more data, compute, or energy. Lowering cross-entropy from about 3.4 to 2.8 nats is very costly. Roughly 10 times more training data is required. Likewise, for large vision models, increasing samples from 1 to 2 billion typically yields only a few percentage points of ImageNet improvement, a clear sign of diminishing returns. See Chapter 3 for cross-entropy and the meaning of nats. Even modest shifts in training metrics, like dropping cross-entropy from 3.4 to 2.8 or a couple of points of ImageNet accuracy, can produce noticeably different downstream behavior. These small numeric improvements often cross internal thresholds that affect translation quality, summaries, or classifier robustness. In this section, we'll examine scaling extrapolation, how model performance and behavior are projected as compute, data, or model size increase. We'll highlight common assumptions, risks, and practical approaches for making cautious forecasts beyond observed data. A model's performance depends heavily on its hyperparameters. With small models, you can afford to train many times and search for the best set. But for large models, even a single training run is resource-intensive, so wide hyperparameter sweeps are usually impractical. We'll define the difference between parameters, the values a model learns from data, and hyperparameters, the settings you choose before training. This distinction guides how we train, tune, and interpret models. Parameters are the model's internal values, the weights that training adjusts to fit the data. Hyperparameters are set by the user before training. Some define the model itself, number of layers, model dimension, vocabulary size, and others control learning behavior, batch size, epochs, learning rate per layer, initial variance. Choosing good hyperparameters changes how quickly and how well the model learns. When you often get only one real chance to train a large model, choosing hyperparameters becomes critical. Scaling extrapolation studies how hyperparameter effects change with model size by testing smaller models and then predicting which settings will work for the target large model. For example, a 2022 Microsoft/OpenAI study transferred hyperparameters from a 40M model to a 6.7B model. Scaling extrapolation is still a niche area because only a few groups have the compute and experimental bandwidth to train very large models. The core difficulty is that hyperparameters interact combinatorially. With 10 hyperparameters, you already face 2 to the power of 10 equals 1024 combinations, and fully understanding effects requires probing each parameter alone and in every pair, triple, and so on, which quickly becomes impractical. Emergent abilities are capabilities that only appear once models or datasets reach a certain scale and may be absent in smaller models. Because of that, extrapolating performance from small-scale runs can be misleading. Trends can change, or new behaviors can emerge. For more detail, see Wei et al., 2022, and Luke Metz's blog post on the difficulty of extrapolation with NN scaling. Now we'll examine the common bottlenecks that prevent systems from scaling smoothly. You'll learn the main categories: CPU, memory, I/O, network, and architectural limits, and how to prioritize diagnostics and fixes. GPT-1 had about 117 million parameters, GPT-2 about 1.5 billion, is almost equal to 10 times, and GPT-3 about 175 billion, is almost equal to 100 times versus GPT-2. That's roughly a 1,000 times increase between 2018 and 2021, and another 3 orders of magnitude of growth would put models on the order of 100 trillion parameters. We don't know how many more orders of magnitude models can grow, or whether performance will eventually stop improving with size. 2 practical limits already stand out: the supply of high-quality training data. Larger models need more and more diverse examples, and the electricity required to run massive training clusters, which increases cost and environmental impact. Those constraints can create an effective performance plateau, even if model architectures keep improving. Foundation models are trained on enormous amounts of web content, and dataset sizes have been growing faster than new data is created. Researchers warn we may exhaust publicly available internet data in a few years. Villalobos et al., 2022. Practically, that means anything you put online should be treated as likely to end up in some model's training set, whether you consent or not, much like public pages being indexed by search engines. This plot shows measured data over some input. Focus on the overall trend first. Then note the scatter around the trend, measurement noise, any outliers, and gaps in the sampling, since these features will affect how we model or fit this data. This figure projects the historical trend of training dataset sizes alongside the total available data stock. We'll use it to examine whether data availability will keep pace with future model scaling. Some attackers deliberately publish specific text on public websites, hoping it will be scraped into future training sets and bias model behavior. This data poisoning technique can be used to steer model outputs or to enable prompt injection attacks that manipulate downstream systems. A brief note before we proceed. This highlights an important detail or assumption that affects later steps. Keep this exception in mind as we continue. An open research problem is how to make a trained model forget specific information. For example, if you published a blog post and later deleted it, but that post was used in training, the model might still reproduce the content, allowing others to access material you removed without your consent. We need techniques to remove such data from models without retraining from scratch. The web is rapidly filling with AI-generated material, so training future models on raw web data will often mean they learn from earlier models' outputs. A concrete example: when Grok refused a request by citing OpenAI's policy, people suspected it had been trained on ChatGPT. A Grok developer replied that the model was trained on web data, and the web already contains many ChatGPT outputs. Some researchers, e.g., Shumalov et al., 2023, found that repeatedly training models on AI-generated data can make them drift away from original data patterns, effectively forgetting earlier distributions. But the real impact depends on how much synthetic data is used, its diversity and quality, and any filtering or mixing strategies. We'll examine these nuances in Chapter 8. Once public sources are exhausted, teams will turn to proprietary, human-generated datasets. Copyrighted books, translations, contracts, medical records, genome sequences, and so on. Those unique collections can give firms a lasting edge, which is why companies like OpenAI negotiate licensing deals with publishers and media outlets. After ChatGPT emerged, sites like Reddit and Stack Overflow changed their terms to prevent external scraping. Longpre et al., 2024, measured the effect. Between 2023 and 2024, Over 28% of C4's most critical web sources became fully restricted, and overall TOS and crawling changes now put roughly 45% of C4 off-limits. This substantially reduces the publicly usable web data for training large models. Machines need electricity, and data centers already consume a non-trivial share of global power. Estimates put current usage at about 1 to 2% and project 4 to 20% by 2030. Without a major increase in energy supply, data center capacity can only expand roughly 50-fold, which risks a near-term power shortage and higher electricity costs. We've covered architecture and scale. Now we shift to alignment, the design choices that make a model's behavior match human preferences and values. This includes methods like reward modeling and RLHF, plus evaluation and trade-offs between capability and safety. In this section, we'll cover the key post-training steps that prepare a model for production. We'll focus on evaluation, validation checks, monitoring, and practical deployment considerations to keep models reliable and safe. Post-training starts from a pre-trained foundation model and exists to fix two common issues. Self-supervised pre-training optimizes for predicting or completing text, not for holding conversations, and models trained on indiscriminately scraped web data can produce biased, toxic, or simply incorrect outputs. Post-training adapts the model for conversational behavior and reduces harmful or wrong outputs. Models vary, but post-training commonly breaks into two main phases. In the next slides, we'll unpack each phase, what it does, and why it matters for model behavior. This is the first step, the starting point for the procedure we'll follow. I'll state the goal here and then show the concrete actions needed to proceed. Supervised fine-tuning takes a pre-trained model and trains it on curated instruction, response pairs, so the model learns to follow prompts instead of just predicting the next token. This shifts behavior toward helpful, conversational replies by optimizing on high-quality, human-crafted instruction data. Start by clearly stating the problem and the specific quantity you want to find or prove. Introduce any variables and notation you'll use. Then give a one-line outline of the plan you'll follow. Preference fine-tuning further trains a model so its outputs match human preferences. Practically, this is treated as a reinforcement learning problem where the model is rewarded for responses humans prefer. Common approaches are RLHF, used in GPT 3.5 and Llama 2, DPO, direct preference optimization, used in Llama 3, and RLHF, reinforcement learning from AI feedback, used in some Claude workflows. Pre-training teaches the model to predict the next token, improving token-level accuracy, but not directly optimizing whole response quality. Post-training adjusts the model to produce responses people prefer, so it teaches the model how to use its knowledge to give better complete answers, like reading to acquire facts versus practicing to apply them. This section calls out important limitations and safety concerns you must keep in mind. Pay close attention to these points before you proceed, as they help you avoid common mistakes. The phrase instruction fine-tuning is used inconsistently. Some authors mean supervised fine-tuning, while others include both supervised and preference fine-tuning. To prevent misunderstanding, this book avoids using that term and uses more specific labels instead. Pre-training takes the lion's share of compute. InstructGPT used roughly 98%, while post-training was only about 2%. That small additional step doesn't invent new abilities. It configures and surfaces capabilities the model already learned during pre-training, which are difficult for users to access through prompting alone. This diagram shows the typical pipeline: large-scale pre-training, supervised fine-tuning, SFT, and a final preference fine-tuning step, often done with RLHF. To estimate how well a model aligns with human preferences, check which of these steps were performed and how thoroughly the creators applied preference tuning. This diagram shows a typical data analysis workflow: data collection, pre-processing, modeling, evaluation, and deployment. Notice the arrows that indicate the sequence and any feedback loops from evaluation back to pre-processing. Those loops show the iterative nature of improving models. Look for where data and model artifacts move between stages, since those handoffs are important for reproducibility and monitoring. This figure gives an overview of the three-stage training pipeline: large-scale pre-training, supervised fine-tuning, SFT, and reinforcement learning from human feedback, RLHF. We'll use this section to follow how data, human labels, and reward models shape the model at each stage. If you squint, the arrangement of shapes in Figure 2.10 looks a lot like the Shoggoth with smiley face meme shown in Figure 2.11. This is a playful visual comparison that highlights how familiar patterns can appear across unrelated images. Begin by clearly stating the single main idea you want the viewer to take away. Keep this claim concise and explain quickly why it matters. Save supporting details for the next steps. Pre-training a model self-supervised on massive, uncurated internet data can produce an untamed or rogue-seeming model because it absorbs whatever patterns and content are present in that data. This raises real risks, inherited biases, privacy leaks, and surprising behaviors, which is why careful data curation and downstream safeguards are essential. For the first point, clearly state the problem and the outcome you want. Defining the goal up front focuses your steps, helps decide what information matters, and prevents you from solving the wrong problem. After pre-training, the model is supervised fine-tuned using cleaner, higher quality sources like Stack Overflow, Quora, and curated human annotations. This teaches the model to prefer safer, more helpful responses and to avoid low-quality or socially problematic outputs. Begin by stating the problem or the specific outcome you want to achieve. A clear goal narrows your options and makes it easier to choose methods and measure progress. Preference fine-tuning is a follow-up training step where human feedback or reward model nudges the model toward responses people prefer. The process tunes tone, helpfulness, and safety so outputs match customer expectations. Think of it as giving the model a friendly, reliable smile. Look closely at the exaggerated proportions, asymmetrical limbs, and the textured line work. These design choices create personality and a clear silhouette. Also notice the high contrast outlines and simplified anatomy that keep the character readable even at small sizes. Here is Figure 211, a playful rendition of a Shoggoth bearing a smiley face, adapted from an image shared by an Anthropad. We'll refer to this figure to discuss visual reinterpretation and proper attribution. A common pipeline for foundation models is pre-training, then supervised fine-tuning, SFT, and finally preference fine-tuning. That combination works well in many cases, but you can omit one or more stages depending on your data, compute budget, or objectives. We'll look at examples soon. In this section, we'll introduce supervised fine-tuning, training a pre-existing model on labeled examples to improve task performance. We'll cover what it means, why it's useful, and the typical workflow. These models are trained to predict the next token, so they treat your input as something to continue rather than as a conversational turn. For example, if you type, "how to make pizza," the model will simply continue that prompt. It might produce step-by-step instructions, ask a clarifying question, or generate an unrelated completion, unless you explicitly frame the exchange as a dialogue. This marks the first item. We're about to state and analyze it. I'll present the claim and then walk through the reasoning step by step so you can follow each part. Here we add the qualifier for a family of 6. That simple detail changes recommended serving sizes, total cost, and scheduling. So always include household size when asking about quantities or budgets. Begin by reading the problem slowly and fully. Know what information is given, what you're asked to find, and any constraints or special notation before you start solving. When you ask for instructions, add concise follow-up questions that surface practical details, ingredients, total time, and key prep steps. Doing this turns a vague answer into a clear, usable plan. Begin by identifying exactly what the problem asks and list any assumptions. Clarifying the goal and the known information up front makes every subsequent step easier and less error-prone. We'll walk through a clear, reliable process for making pizza at home. Prepare the dough, spread the sauce, add toppings, and bake. I'll point out timing, oven temperature, and quick tips for a crisp crust and even cooking. Since the goal is to respond to users appropriately, option 3 is the right choice. It best balances accuracy, helpfulness, and tone. The other options either risk incorrect detail, unnecessary verbosity, or a mismatched tone. Because models tend to mirror their training data, the most direct way to steer them is to show examples of the behavior you want. Those examples are pairs of prompt, response, called demonstration data or behavior cloning, and the model learns to imitate those responses. Your demonstration examples should cover the range of requests you want the model to handle. For example, question answering, summarization, and translation. OpenAI's InstructGPT was fine-tuned with a specific task distribution. See Figure 2.12, and because InstructGPT is text-only, that distribution does not include multimodal tasks. This circular diagram groups related AI engineering ideas into color-coded segments. Look at how each color and label creates a quick visual category, and check the center or connecting lines to see any core theme that ties the segments together. Use the color and placement to infer relationships at a glance. This figure presents the distribution of prompt types used to fine-tune InstructGPT, reconstructed from the counts reported in the OpenAI paper. We'll use it to see which prompt categories were most common and how that shapes the model's behavior. Treat labelers as teachers for conversational AIs. Creating demonstration, prompt, response pairs often requires research, domain knowledge, and ethical judgment. So these examples are more complex than ordinary labels. Table 2.6 shows concrete examples used to train InstructGPT. This table displays prompt, response pairs written by human labelers to show InstructGPT what good outputs look like. Examples range from a single sentence usage of a word, to multi-question reading comprehension answers, to an ELI 5 explanation of a physiological feeling, covering clarity, brevity, and audience-appropriate tone. Companies often use highly educated labelers for demonstration data. For InstructGPT, about 90% had college degrees and over a third held master's degrees. Producing one prompt response pair can take up to 30 minutes. At roughly $10 per pair, 13,000 pairs cost around $130,000. That figure doesn't include extra expenses like choosing tasks and prompts, recruiting labelers, or quality control. To cut costs, LAION recruited 13,500 volunteers who produced 10,000 conversations, 161,443 messages, and 461,292 quality ratings across 35 languages. Because contributors were volunteers rather than a demographically controlled sample, the label pool is skewed. A survey found 90% identified as male, which can introduce bias into any model trained on these preference labels. To train Gopher, DeepMind applied simple rule-based heuristics to large web data to pull out conversational passages. They look for text that reads like turn-taking, lines with speaker labels, e.g. user, assistant, short back-and-forth turns, or clear question-answer structure, and treated those examples as higher-quality dialogue data. This code block is a simple template for an alternating two-speaker dialogue, where each line starts with a speaker label in brackets, A or B, followed by a short paragraph placeholder. When you use it, replace each short paragraph with the actual utterance for that speaker. The ellipsis shows the pattern repeats. Think of it as a script skeleton that enforces turn-taking between two participants. To cut the cost and bottleneck of hand-labeled examples, many teams now generate synthetic data using models or programmatic rules. This approach can scale training sets quickly, but requires careful validation and calibration of the synthetic labels. Chapter 8 covers dataset engineering and practical trade-offs. You can skip self-supervised pre-training and train a model only on the demonstration data. However, large-scale pre-training usually produces more robust features and higher final performance, especially when demonstration data is limited. Now we'll introduce preference fine-tuning, a technique that adjusts a model using human preferences or feedback rather than only supervised labels. We'll outline what it does, why it's useful, and the high-level workflow you'll see next. Powerful models can enable great achievements and also enable serious harm. Demonstration data teaches a model how to hold a conversation, but it doesn't teach the model which conversations are acceptable. That's why we need explicit safety policies to refuse requests that promote harm, hate, or dangerous instructions. Many real-world questions, for example about abortion, gun control, immigration, or economic policy, divide people across cultural, political, and personal lines. That means models must balance trade-offs. Whatever stance they take will upset some users, but over-censoring makes the system unhelpful. We therefore need principled ways to detect controversy and to design measured, transparent responses. Many companies delay releasing AI products because models can generate inappropriate or harmful responses. Preference fine-tuning tries to steer models toward what humans prefer, but it's a very ambitious goal. It assumes a single, knowable human preference exists and that we can fully encode it into a model. A simple objective could have a loud and elegant fix, but the ambition of aligning large models makes the practical solution more complicated. The earliest widely used method is RLHF. First, we train a reward model from human preference labels. Then we apply reinforcement learning to optimize the model's policy to maximize that learned reward. This marks the first point we'll address. I'll introduce the main idea here and then unpack the details in the following steps. Train a separate reward model that assigns a quality score to each output produced by the foundation model. The reward model is trained from human preferences or labeled examples and provides a learned objective for ranking outputs or for later optimization of the generator. Start by clearly stating the problem you want to solve. A precise problem description specifies the inputs, the desired outputs, and any constraints so your next steps are unambiguous. We update the foundation model so its outputs get the highest possible scores from a separate reward model. This encourages the model to produce behaviors the reward model values, but can also incentivize gaming if the reward model is incomplete or misspecified. DPO, Rafaelov et al., 2023, is a newer, simpler alternative that's gained traction. Meta switched from RLHF for Llama 2 to DPO for Llama 3 to reduce complexity. I present RLHF here because, although more complex, it provides greater flexibility to fine-tune behavior and was argued by the Llama 2 authors to help produce superior writing. We'll define the reward model and show how it turns human feedback into a scalar score used to train and evaluate policies. Understanding this component is key to grasping preference learning and reinforcement learning from human feedback. In RLHF, a reward model assigns a score to each prompt response pair, and we train models to predict those scores. Collecting reliable scores is difficult. Different labelers, or the same labeler at different times, will give different numbers, so evaluating each sample independently, point-wise, produces noisy labels. A common, easier annotation task is pairwise comparison. Labelers see two responses for a prompt and choose the better one, producing tuples like prompt, winning_response, losing_response. Because responses can come from humans or models and people disagree, the recorded winner may not match another person's preference. This shows why it's hard to capture diverse human preferences with a single mathematical objective. This is a real comparison from Anthropic's RLHF dataset. For the provocative prompt about getting a dog high, annotators preferred the short clarification, "I'm not sure what you mean by that," over a longer, explicit refusal. It shows that preference labels can favor concise, clarifying, or redirecting responses rather than extended, moralizing explanations. Even a simpler task like comparing two model answers still takes time, because you have to fact-check both responses. LMSYS measure about 3 to 5 minutes per comparison, and Thomas Asylum reported a cost of roughly $3.50 each. That's substantially cheaper than generating full responses, which can cost around $25 a piece. Annotators use a UI that shows numeric scores, but the important signal for training the reward model is the ranking of responses. About 73% interlabeler agreement means roughly 7 out of 10 annotators give the same ordering. To label more efficiently, annotators rank multiple responses at once, and each ranked set generates all pairwise comparisons used for training. This image is a screenshot of a computer screen, and it's actually a screenshot of a screenshot. As you look, notice the nested frames, window chrome, title bars, and toolbars, and any highlighted areas that show where attention was focused. Pay attention to scaling and compression artifacts that can reduce sharpness and legibility. This figure shows the labeling interface used to collect comparison data for OpenAI's InstructGPT. We'll briefly note what labelers saw and how their selections produce the preference signals used to fine-tune model behavior. With only pairwise comparisons, we teach the model to output scalar scores by rewarding higher scores for chosen responses and lower scores for rejected ones. InstructGPT implements this by passing the score difference through a sigmoid, a Bradley-Terry-style probability, and maximizing the log probability of the winner, which pushes the winner's score up and the loser's down. R_theta is the reward model we train. We update the parameters theta to minimize the loss, so the model gives higher scores to preferred outputs and effectively guides downstream policy learning. If a task looks overwhelming, pause and strip it down to its core components. Isolate the essential variables, solve a simpler version to build intuition, then reintroduce the removed details. This stepwise simplification keeps reasoning clear and reduces mistakes. This section defines the exact structure your training dataset must use so loaders, preprocessors, and the model all agree. Pay attention to which fields each example must include, their data types, and any required ordering or delimiters. Here, X denotes the prompt given to the model. It's the input that determines what the model has to work from, so precise prompts lead to clearer, more relevant outputs. Here, Y_W denotes the winning response, the reply judged best among the candidates. We care about Y_W because it serves as the target for reward calculations and model updates. Misidentifying it changes the learning signal. Y_L denotes the losing response, the model output judged inferior in a pairwise comparison. We record it so we can analyze failure modes and compare it to the winning response during evaluation and fine-tuning. S_W is the single scalar produced by the reward model when it evaluates the input X together with the chosen reply Y_W. This score is what we use to compare and rank candidate responses. It gives a quantitative measure of how good the winning reply is according to the reward model. This symbol denotes the scalar score the reward model assigns to the losing candidate in a comparison. We use S_L together with the winner's score to compute pairwise losses and gradients that teach the model to prefer better responses. Here sigma denotes the sigmoid activation sigma. X equals 1/1 plus e caret x. It squashes any real input into the range 0, 1, which makes it useful for modeling probabilities and for gating signals in neural networks. For each example, we compute a scalar loss from the input X and its paired labels Y_W, winner, and Y_L, loser. The loss quantifies how much the model prefers the incorrect label over the correct one, and is what we minimize to update the model. This is the log of the sigmoid applied to the difference between the model scores for the correct label Y_W and an incorrect label Y_L. Using log sigma of the score margin gives a smooth, differentiable loss that behaves like a log likelihood and improves numerical stability during training. Summarize the main claim in one clear sentence. Give a quick intuition or simple example that makes the claim believable, and then state why it matters or what to check next. This pattern keeps explanations concise and actionable. We want to find the model parameters theta that make our predictions as good as possible on average. Practically, that means minimizing the expected loss or risk computed across the training distribution so the learned model generalizes well. This is the expected log sigmoid of the score difference between a preferred response y_w and a less preferred response y_l. It matters because maximizing this term pushes the model to give higher scores to better outputs, effectively teaching a margin between preferred and non-preferred responses. Reward models can be trained from scratch or fine-tuned on top of another model. In practice, fine-tuning on a strong foundation model usually gives the best results. It's a common belief that the reward model must be at least as powerful as the foundation model, but judging is often easier than generating, so a weaker model can sometimes reliably evaluate a stronger one. In this section, we'll learn how a trained reward model is used to fine-tune a policy model. I'll outline the intuition, why a reward model provides better training signals, and the common ways it's applied in supervised and reinforcement-style fine-tuning. We take the trained reward model and further fine-tune the SFT so its responses get higher RM scores. Training samples prompts, often real user prompts. The model generates responses that the RM scores, and the SFT policy is updated using proximal policy optimization, PPO, the RL method OpenAI introduced in 2017. Empirically, both RLHF and DPO usually improve over supervised fine-tuning, SFT, but researchers still debate the underlying reasons. Expect preference fine-tuning methods to change as the field matures. For code and references, see the book's GitHub repository. Supervised fine-tuning, SFT, and preference fine-tuning are extra training steps we use because pre-training data is often noisy or misaligned with user goals. These steps correct and align a foundation model's behavior. If pre-training data and methods improve enough, we might not need them. Some companies stitch fix and grab, for example, skip reinforcement learning and rely on a reward model instead. They generate many candidate outputs, score each with a reward model, and pick the high-scoring one. This best of N approach leverages sampling diversity to boost quality without an RL training loop. We'll start by defining sampling, how we convert continuous time signals into discrete sequences. In this section, you'll learn why sampling matters and the basic techniques and pitfalls to watch for. A model produces text by sampling tokens from its predicted probability distribution. We control the process with sampling variables like temperature, top K, and top P to adjust randomness and focus. Drawing multiple samples and re-ranking them often improves results, and the sampling process can be constrained to force specific formats or hard rules when needed. When a model uses sampling to generate text, each reply is drawn from a probability distribution, so you can get different outputs for the same prompt. This probabilistic behavior explains why models can be inconsistent or produce hallucinations. Next, we'll dive into what that means and how to work with it. We'll cover the core ideas behind sampling, how continuous time signals become discrete sequences, what sampling rate means, and why aliasing occurs. You'll also learn practical rules like the Nyquist criterion and how to choose a safe sampling rate. A classifier doesn't directly give a final label. It computes a probability for each possible class. To make a decision, you apply a rule, like a threshold. If spam probability greater than 50% mark as spam, so a 90% spam score becomes spam. To generate the next token, the model scores every vocabulary entry and converts those scores into a probability distribution. That's what the figure illustrates. The model then chooses a token either by picking the highest probability option or by sampling according to these probabilities. Study the diagram for how colors are arranged and grouped, and pay attention to any arrows or labels that indicate relationships or transitions. These visual cues show how hues, shades, or semantic categories relate to each other and help map the concepts we're discussing. This section shows how a language model produces the next token by assigning a probability to every token in its vocabulary. We'll outline how that probability distribution is computed and how it's used to choose the next output, e.g., argmax, or sampling. Choosing the single most likely outcome is called greedy sampling. It usually works for classification. If P, spam, P, not spam, label it spam, but for language models, it makes output boring and repetitive because the model keeps picking the most common words. Rather than always picking the single most likely token, the model can randomly sample the next token according to its predicted probabilities. For example, after my favorite color is if red has 30% probability and green 50%, then red will be selected about 30% of the time and green about 50%. This stochastic choice produces more varied, less deterministic outputs. The model's neural network outputs a logit vector, a raw score for every possible token in the vocabulary. Those logits are converted into a probability distribution, typically with softmax, so the vector length equals the vocabulary size, and each logit maps directly to one token. Look at how nodes are grouped and how many links each node has. Identify dense clusters and any highly connected hubs. Pay attention to isolated nodes or single links that could create bottlenecks or single points of failure. These are important when assessing traffic flow and system resilience. This figure shows that for every input, the language model computes a logit for every token in its vocabulary, producing a logit vector. Those logits are then converted into probabilities, typically via softmax, to choose the model's next token. Logits are raw model scores. Bigger logits imply higher likelihood, but they are not probabilities. They can be negative and do not sum to 1. To convert a logit vector x1, xn, into probabilities, we apply softmax. P underscore I equals exp x underscore slash sum of exp x underscore j, which exponentiates each score and then normalizes by the total. Softmax turns a vector of raw scores x into a probability distribution p. It exponentiates each score to make larger values stand out, then divides by the sum of all exponentials, so every p underscore I is positive and the probabilities sum to 1. In this section, we'll examine common sampling strategies used in statistics and machine learning and why we choose them. We'll focus on the trade-offs for random, stratified, systematic, and cluster sampling, and when each is most appropriate. The sampling strategy you choose changes how a model composes text. Some strategies encourage creative, diverse outputs, while others make generations more stable and predictable. There are many established methods, and you can build custom samplers too if you can access the model's logits. We'll now look at a few common strategies and how they influence outputs. We're starting a section on temperature. We'll define what temperature measures, distinguish everyday and thermodynamic meanings, and outline why it's central to equilibrium and heat flow. If we pick each next token exactly according to its probability, common words like red or green tend to win. That makes the model give safe, predictable replies. For example, my favorite color is green, and sharply reduces the chance of more imaginative continuations like the color of a still lake on a spring morning. Temperature is a knob that reshapes the model's probability distribution. Raising temperature flattens the distribution, so common tokens lose dominance and rarer tokens become more likely, which tends to produce more surprising or creative outputs. Lower temperatures make the model more conservative and repeat common choices. Temperature is a scalar t that divides each logit before we apply softmax. The adjusted logit is x underscore I slash t. This scaling changes the distribution shape. Larger t makes probabilities more uniform, softer, smaller t makes them peakier, sharper. After scaling, we apply softmax to the adjusted logits to obtain the final probabilities. We'll use a tiny model with only two outputs, A and B, to see how temperature changes probabilities. The model's final layer logits are 1 for A and 2 for B. These are the raw scores we'll convert to probabilities and then modify by different temperatures. Using temperature 1, the default softmax produces probabilities 0.27, 0.73. If we sample from this distribution, the model will pick token B about 73% of the time, while token A still has a 27% chance. Lowering temperature to 0.5 5 sharpens the softmax, so the higher scoring token B receives most of the probability mass. With probabilities 0.12, 0.88, the model will sample B about 88% of the time and A about 12%. Temperature risk scales the model's logits before sampling. A higher temperature flattens the probability distribution, so the model is less likely to always pick the top logit token and produces more varied, but sometimes less coherent, outputs. A lower temperature sharpens the distribution, so the top logit choice is much more likely, yielding consistent but potentially boring results. Temperature risk scales logits before the softmax. Low temperatures sharpen the distribution, so the top token dominates, while higher temperatures flatten it and increase variety. In this example, as T approaches 0, the model almost always picks token B. Below 0.1, it's nearly certain. Increasing T raises A's probability and lowers B's. Providers typically limit T to 0, 2. If you run your own model, any non-negative T is allowed. Try 0.7 as a starting point for creative tasks, and then experiment. This plot shows a single line across a coordinate plane. Look for the line's direction and steepness, the slope, where it crosses the axis, intercepts, and whether the relationship looks strictly linear or has any deviations. This figure compares the softmax probabilities for tokens A and B when their logits are 1, 2. Note that with the default temperature of 1, token B has about a 73% probability. The plot shows how changing temperature redistributes those probabilities. Technically, you can't divide logits by 0, so temperature can't be literally 0. In practice, setting temperature to 0 makes the model deterministically choose the token with the largest logit. It skips softmax and any sampling and just performs an Rmax. Here's a quick practical tip to make the next steps easier and safer. I'll point out the common pitfall and a simple habit that prevents it. A quick, practical debug is to inspect the probabilities the model assigns to tokens or labels. If those probabilities look essentially random, uniform, or noisy across different inputs, the model probably hasn't learned meaningful patterns. This check often points to issues with training data, optimization, or model capacity. Log probs are probabilities represented on the logarithmic scale. Models use them because many individual token probabilities, for example with a 100,000 item vocabulary, can be so tiny they underflow to 0 in normal scale. Logs keep those values representable and numerically stable. The figure shows the step-by-step conversion of model outputs into usable scores. A model emits logits. Softmax converts those logits into a probability distribution, and taking the log of those probabilities yields log probs used in loss calculations and for numerical stability. This diagram shows how softmax turns raw scores, logits, into a probability distribution. Notice the exponentiation of each score followed by a normalization by the sum that yields non-negative outputs that sum to 1, which we use for classification and probabilistic interpretation. This figure walks through the numerical steps that turn raw model outputs, called logits, into normalized probabilities and then into log probabilities. We'll briefly highlight the softmax normalization and why converting to log probs matters for loss calculation and numerical stability. Log probs are very useful for classification, evaluation, and for understanding model internals. Many providers don't expose full log probs, or they offer a restricted log probs API, likely because detailed token probabilities can make it easier to replicate or attack a model. Now we'll study top case sampling, a decoding method that limits the model's next token choices to the k most probable options. We'll see how this changes randomness and coherence, and when to prefer it over other strategies. Softmax computes probabilities by first summing exponentials across the entire vocabulary, and then dividing each exponential by that sum. Effectively 2 full passes over all tokens. For very large vocabularies, this becomes computationally expensive. Top case sampling speeds inference by restricting those computations to only the k most likely tokens, cutting cost while largely preserving response diversity. Once the model produces logits, we keep only the top K logits and apply softmax to that smaller set. The model samples from this limited distribution instead of the whole vocabulary. A smaller K, around 50, makes output more predictable, while a larger K, up to 500, increases diversity and interest. Now we'll examine top P sampling, also called nucleus sampling. It chooses from the smallest set of tokens whose cumulative probability exceeds P, giving a controlled balance between diversity and coherence. Top K sampling traditionally fixes the number of candidate tokens, but that number should depend on the prompt. For a strict yes/no prompt, you only need K equals 2, just yes and no. For an open-ended question, you want a much larger K to allow many plausible continuations. Top P, or nucleus sampling, builds a dynamic candidate set by sorting next token probabilities and keeping the top tokens until their cumulative probability reaches P. The model then samples from only that set, so the number of considered tokens changes with confidence. For example, P equals 0.9 means we keep the smallest group of tokens whose probabilities add up to at least 90%. Top P, or nucleus sampling, sorts tokens by probability and includes the smallest prefix whose cumulative probability meets the threshold P. Using the probabilities in Figure 218, a 90% threshold includes only yes and maybe, while raising the threshold to 99% also lets no into the candidate set. This screenshot shows a computer screen capture. Focus on the overall layout and the primary UI elements visible. Look for window arrangement, any highlighted text or controls, and whether text and icons are legible for documentation or analysis. This figure presents an example distribution of token probabilities from a language model for one prediction step. We'll use it to see how probability mass gets allocated and how that affects which token the model is likely to pick next. Top P doesn't necessarily cut the softmax computation because it still evaluates token probabilities. Instead, it selects the smallest set of tokens whose cumulative probability reaches the threshold P. By adapting the number of candidates to each context, Top P tend to produce more contextually appropriate outputs. Its theoretical benefits are subtle, but in practice it often works better than fixed Top K, which is why it's widely used. Min P sets a floor on token probability. Any token whose probability is below the chosen threshold is ignored during sampling. This prevents extremely unlikely tokens from being chosen, while still allowing diverse outputs from the remaining, sufficiently probable options. Now we define the stopping condition, the rule or criterion that tells an algorithm when to halt. We'll outline why a clear stopping rule matters and the common forms it can take. Autoregressive language models produce text one token at a time, so every additional token adds latency and compute cost. Long outputs can also annoy users or waste budget, which is why we often enforce a stop condition to end generation when appropriate. One simple approach is to truncate output after a fixed number of tokens, but that often slices sentences in the middle. A cleaner method is to provide explicit stop tokens or stop words, for example, the model's end-of-sequence token, so it finishes naturally. Using stopping conditions helps control latency and costs by avoiding unnecessary generation. Stopping generation too early can truncate structured outputs. For example, a JSON response might be missing closing brackets or fields, making it invalid and hard to parse. When you require strict formats, be aware of truncation and plan to detect or repair incomplete outputs. We'll define what test time compute means and why it matters for evaluating models during inference. Next, we'll outline the components that add to inference cost and the key metrics to track. Previously, we examined how a model samples one next token. To generate a full output, the model repeatedly samples the next token conditioned on prior tokens until a stop rule, EOS token, max length, etc., applies. The choice of strategy, greedy, temperature scaling, top K, or top P, nucleus, sampling, shapes the output's diversity, coherence, and common failure modes like repetition or premature stopping. One easy way to improve response quality is test time compute. Generate multiple outputs for a single query and pick the best. That's the best event approach. A more strategic option is beam search, which keeps a small beam of the most promising partial sequences at each step so you get fewer low-quality candidates and often stronger final responses. Generating a more diverse set of outputs raises the chance that one will be a high-quality candidate. When you sample from the same model multiple times, change its sampling parameters, temperature, top K/top P, or beam randomness to produce that useful variety. Generating multiple outputs often yields better model performance, but it increases cost and latency. For example, producing 2 samples usually costs about twice as much as producing one, so balance the quality gains against the expense. Before you proceed, note a critical caution that affects the next steps. Pay close attention so you avoid common mistakes and preserve safety and correctness. I use the term test time compute to stay consistent with the literature, even though it can sound confusing at first. It usually means the compute used at inference, what researchers call test time, but the same idea applies when models run in production. We call it test time compute because the number of outputs you can sample is determined by how much compute you allocate to each inference call. One way to pick the best output is to choose the sequence with the highest probability according to the model. The model assigns a probability to each token, and the probability of a complete output is the product of those token probabilities. Comparing these sequence probabilities gives a principled selection among candidate outputs. This uses the chain rule. The joint probability of a sequence equals the product of each token's probability conditioned on the previous tokens. Plugging in the numbers gives 0.2 times 0.1 times 0.3 is equal to 0.006. So the probability of that exact 3-word sequence is 0.6%. This line is illustrating the chain rule for the joint probability of the token sequence. I love food. We decompose the joint into a product of a marginal for the first token and conditionals for subsequent tokens. Each factor represents the probability of a token given the tokens that came before it. Note that the second factor here appears reversed. The standard chain rule ordering would use P, love I, rather than P, I love. We usually compute probabilities on the log scale because logs turn products into sums, which is both numerically stable and easier to manipulate. Concretely, the log probability of a token sequence is the sum of the log probabilities of its individual tokens. This line applies the probabilistic chain rule to expand the joint log probability of the 3-word sequence into a sum of log probabilities. The first term is the marginal log probability of I, and the other terms are conditional log probabilities. Note the middle term conditions on love, a future token, whereas the usual forward chain rule would use log P, love I, then log P, food I, love. If you simply sum token log probabilities, longer sequences usually get a lower total because log probs are negative, which biases selection toward short outputs. Dividing the summed log prob by the sequence length gives the average log prob, a length normalized score. After sampling many outputs, choose the sample with the highest average log prob. This is the method the OpenAI API uses. A common selection method is to rank candidate outputs using a learned reward model, then choose the highest scoring responses. Companies such as Stitch Fix and Grab use this approach, and Nextdoor reported that adding a reward model was the key factor in improving their application's performance. OpenAI trained verifiers that evaluate candidate solutions and pick the best answer, which significantly improves math performance. The improvement was roughly equivalent to increasing model size by 30 times. For example, a 100M parameter model with a verifier performed like a 3B model without one. DeepMind, Snell et al., 2024, shows that using more compute at test time, for example generating many candidate outputs and selecting or re-ranking them, can be more compute efficient than simply increasing model parameters. They pose a concrete question. Given a fixed, non-trivial inference time compute budget, How much can an LLM improve its performance on a challenging prompt? OpenAI found that sampling more outputs improved results only until about 400 samples, after which accuracy declined. They suspect more samples increase the chance of adversarial outputs that fool the verifier. A Stanford paper called Monkey Business instead observed roughly log linear gains as samples increase from 1 to 10,000. But in practice, drawing hundreds or thousands of outputs per query would be prohibitively expensive. Look closely at the blue lines and the numeric labels. Observe their slopes, where the lines intersect, and any peaks or turns. The labels mark key values, so you can compare trends and spot where the behavior changes. OpenAI 2021 measured how model performance changes as you sample multiple outputs. They observed steady improvement when increasing the number of samples, but the benefit plateaus and stops growing after about 400 outputs. Tailor your response selection rules to what the app needs. For instance, if brevity is important, choose the shortest candidate. If you generate SQL, keep sampling until you obtain a syntactically valid query. For slow queries, like chain of thought, you can use extra test time compute to reduce wait time. Run multiple completions in parallel and present the first one that finishes and passes simple validity checks, giving the user a faster response without changing the model itself. When a task needs an exact answer, generate several completions and choose the most frequent result, a majority vote. This reduces randomness and errors. For example, Gemini sampled 32 outputs per MMLU question and selected the most common answer to boost accuracy over a single draw. Robustness means small input changes don't flip a model's output. When a model is brittle, taking multiple independent samples raises the chance of a correct result. For example, an image extraction model only read the needed text about half the time on a single pass, but running 3 attempts per image recovered the correct information for most images. In this section, we'll learn what structured outputs are and why they matter. You'll see simple patterns for defining predictable, machine-readable responses that downstream tools can parse reliably. In production, models must often produce outputs in a predictable format. This is critical when downstream systems or databases need to parse fields reliably, and when outputs must pass validation, auditing, or fit into a fixed UI. So predictable structure reduces errors and simplifies integration. Begin by stating precisely what you need to find and what information is given. Note any constraints or implicit assumptions before you start solving. A clear problem statement prevents wasted steps. Semantic parsing converts natural language into structured, machine-readable outputs. A common example is text to SQL. The model translates an English question into a valid SQL query for databases like PostgreSQL. This lets users query databases or call APIs using everyday language instead of writing SQL by hand. This slide shows a prompt sent to GPT-4o asking it to convert natural language into regular expressions. The examples that follow are the actual outputs produced by the model, which we use to assess accuracy and style. This instruction asks the model to output a single regular expression for a given item using the exact format, item-regex, and nothing else. The examples show common patterns. The US phone regex allows an optional country code, optional parentheses around the area code, using a conditional group and common separators. The email regex is a typical character class-based pattern. The dates regex accepts 1 to 2-digit day, /month with /, or separators, and 2 to 4-digit years. When you implement this, produce only the regex string as the response. Another common task is classification, where the model must pick a label from a predefined set. The important constraint is that every output must correspond to one of the valid classes, so we often constrain or map model outputs to ensure they match that label set. In step 1, identify what is given, what you must find, and any constraints. Choose clear notation for the key quantities so the rest of the solution is easier to follow. Even if the original task doesn't require structured output, Any result consumed by other programs must be machine parsable. Design the output format so downstream applications can reliably read and process it without hand editing or guessing. An AI can generate a free-form email, but a downstream application may require that content in a precise schema. For example, the app might expect a JSON object with keys like title and body, so it can reliably extract and process those fields. In agentic workflows, the model's outputs are often fed directly into tools or later processing steps. That means you must design clear output formats, add validation and error handling, and treat outputs as potentially hazardous. Otherwise, small mistakes can cascade. See Chapter 6. Tools like Guidance, Outlines, Instructor, and Llama.cpp help models produce structured outputs, and providers often add custom techniques too. OpenAI popularized a JSON mode that encourages syntactically valid JSON, but it only guarantees format, not the correctness of the data. Be mindful of the max token setting. Set it too short, and outputs can be truncated, breaking the JSON. Set it too long, and responses become slow and expensive. Figure 220 gives two practical examples of using guidance. One that forces the model to choose from a predefined set of options, and another that requires the output to match a regular expression pattern. These constraints make model outputs predictable and valid, which is important when you need structured or restricted responses. This screenshot shows a typical desktop application layout. Notice the clear split between a header or toolbar, a side navigation column, and the main content area. Look for status indicators, highlighted items, or controls that signal user actions. This figure shows how guidance, prompts, templates, and explicit constraints steers a model toward outputs that meet specific requirements. We'll highlight why guidance narrows the model's output space and how that makes results more predictable and useful. You can steer a model at 5 layers: prompting, post-processing, test-time compute, constrained sampling, and fine-tuning. The first 3 are lightweight bandages. They nudge an already capable model. For robust, systematic structure, you need the heavier treatments: constrained sampling or fine-tuning. We just covered test-time compute, generating repeatedly until one output fits the format. Here we'll examine 4 other strategies that avoid extra generation at inference: prompt engineering, chain-of-thought prompting, output constraints, and post-processing, and model selection or fine-tuning. Each takes a different approach to improve correctness without looping at test time. In this section, we'll focus on prompting, how to write clear instructions that get useful, predictable responses from models. We'll cover core principles, example prompts, and common mistakes to avoid. You can tell a model to produce structured outputs in any format, but whether it follows that instruction depends on 2 things: the model's instruction following capability and how clear your prompt is. Even strong models make occasional format errors, and a few % of invalid outputs can be unacceptable, so plan to validate, filter, or post-process results. One strategy is to run a second AI to validate or correct each generated output, the AI as judge approach from Chapter 3. That extra validation often improves correctness, but means at least 2 model calls per item, increasing both cost and latency and sometimes making the method impractical at scale. Now we begin the post-processing stage, the steps applied to raw model outputs to produce final, usable results. I'll outline common techniques like filtering, calibration, and formatting, and explain when to apply each. Large models often repeat the same mistakes across queries, so small post-processing scripts can catch and fix those predictable patterns at low cost. For example, automatically inserting a missing JSON bracket or running a defensive YAML parser can transform outputs. LinkedIn's parser improved correct YAML from 90% to 99.99%. Bataro and Ramgopal, 2020. A quick practical suggestion to keep in mind: double-check your assumptions before you proceed. This simple habit prevents many common errors and saves time later. Both JSON and YAML are common text formats, and GPT-4 works with either. LinkedIn found YAML produced shorter outputs than JSON, so it used fewer output tokens. A practical win for efficiency and cost, Bataro and Ramgopal, 2020. Post-processing works when a model's outputs are already close to correct. It can reliably repair small, local issues like a missing comma, a wrong tag, or a formatting slip. If outputs contain many errors or the overall structure is wrong, automated fixes usually fail, and you should improve the prompt or use a different model. In this section, we'll examine constrained sampling, methods that steer generative models to satisfy constraints or match a target distribution. I'll outline why constraints matter and the main approaches we'll cover, such as rejection and importance sampling and guided decoding. Constraint sampling steers a language model's outputs toward explicit requirements, such as factual accuracy, formatting, or content restrictions. Practically, it's used as a pre-filter or steering step and is typically followed by structured output tools like constrained decoders, validators, or programmatic post-processors to enforce the constraints fully. To generate a token, the model first produces a logit for every possible token. Constrained sampling filters that logit vector to remove or disable any tokens that violate the constraints, then draws the next token from the remaining valid options. This guarantees the sampled token meets the specified constraints. Look at this diagram of a software model. Focus on the major components, the arrows that show data flow between them, and any highlighted dependencies or feedback loops that indicate where changes propagate. This figure shows how we remove, mask, logits that violate constraints, so sampling only happens among valid tokens. We'll use this section to understand how filtering changes the distribution before the sampler picks an output. Simple constraints can be filtered directly, but most situations need a grammar that defines what tokens are allowed at each step. For example, JSON grammar prevents an unescaped immediately after another. The only way to have there is inside a string, as in string. A parser enforces these rules to accept or reject the next token. Creating and integrating a grammar for each output format, JSON, YML, regex, CSV, and so on, is non-trivial, so constraint-based sampling doesn't generalize across formats and only applies where grammars and supporting tools exist. Verifying outputs against those grammars also increases generation latency, which further limits practical use. Brandon T. Willard, 2024. Some argue that resources spent on enforcing constraints at generation time would be better invested in training models to follow instructions more reliably. The idea is that a model that understands instructions natively is simpler to deploy and avoids the engineering overhead of constraint enforcement. This section explains fine-tuning, when and why to adapt a pre-trained model. You'll learn the core steps, dataset preparation, training choices, and evaluation, and practical tips to avoid common pitfalls. Fine-tuning a model on examples that follow your target format is the most effective and general way to make it produce that format. This approach works for any expected structure and is much more reliable than trying to coax formats with prompts, though it doesn't absolutely guarantee perfect outputs every time. You can enforce an output format by changing the model's architecture before fine-tuning. For classification, that means attaching a classifier head on top of the foundation model, so it can only output one of the pre-specified classes, a technique often called feature-based transfer and covered further in Chapter 7. This diagram depicts a single neural network layer. Notice the inputs on the left, the weighted connections into the neurons, the bias and activation step inside the layer, and the resulting outputs on the right. That flow shows how raw inputs are transformed into activations. Now we'll attach a classifier head to the base model so it produces class scores instead of raw features. This figure uses a 3-class head to illustrate how feature vectors are mapped to class probabilities. You can fine-tune either the entire model end-to-end or only part of it, such as the classifier head. End-to-end fine-tuning typically requires more compute and memory, but often gives better performance, while training just the head is faster and cheaper. We use special methods because current models often struggle to produce exact, structured formats by themselves. As models get better at following instructions, minimal prompting should suffice more often, so these techniques will likely matter less over time, though they'll still be useful during the transition. In this section, we'll examine why AI outputs are fundamentally probabilistic rather than deterministic. We'll highlight what that implies for response variability, confidence measures, and how to interpret model answers in practice. Many AI models don't always give the same answer because they sample from a probability distribution. For example, if a model gives Vietnamese cuisine a 70% probability and Italian 30%, it will say Vietnamese about 70% of the time and Italian about 30% of the time. A deterministic system would instead produce the same answer every time with no randomness. Because these models sample from learned probabilities, they can behave inconsistently and sometimes state facts that aren't true. Inconsistency means the model gives different answers to the same or similar prompts. Hallucination means the model confidently proposes information that isn't grounded in reality. For example, if a false essay claiming all U.S. presidents are aliens was in its training data, the model might later assert that the current president is an alien. These models learn a statistical distribution from vast, diverse data, so their outputs reflect an aggregation of language patterns and opinions. That means anything with non-zero probability, even very unlikely or incorrect statements, can be produced, so treat outputs as possibilities, not guaranteed facts. Models produce likely answers, not guaranteed ones, and that uncertainty makes AI development both powerful and challenging. AI engineering focuses on harnessing this flexibility and reducing unwanted variation through evaluation, calibration, and safety measures. Modern AI samples from probability distributions, which makes it excellent at exploring surprising combinations, a powerful sidekick for brainstorming and generating novel designs. The flip side is that the same probabilistic behavior can produce unpredictable or incorrect outputs when you need exactness, so apply verification and constraints for non-creative tasks. In this section, we'll define inconsistency and why it matters in statistics and logic. You'll see how an inconsistent method can produce misleading or unstable conclusions, and how to recognize it in practice. Model inconsistency shows up in two common ways. One is between model inconsistency. Different models or versions behave differently on the same task. The other is within model inconsistency. The same model gives different outputs when prompts are paraphrased, reformatted, or because of randomness. Begin by reading the problem carefully and identifying what is given and what you need to find. Circle key numbers, assign variable names, and restate the question in your own words so the goal is clear. Running the exact same prompt multiple times can produce very different responses. Most generative models sample tokens probabilistically, temperature, top K, /top P, and random seeds introduce non-deterministic variation. If you need repeatable output, use deterministic decoding, greedy, or fixed beam, or set a fixed random seed. Begin by reading the problem carefully and asking, what exactly is being asked? Identify the given information, any constraints, and implicit assumptions so you can choose the right approach. Even a very small change to a prompt, an extra character, different punctuation, or capitalizing a letter, can produce a markedly different model reply. Models are sensitive to wording and tokenization, so small edits can shift the probabilities and lead to surprising outputs. I ran the identical essay scoring prompt twice and got two different results, once March 5th and once May 5th. This illustrates model non-determinism and why single-run automated scores can be unreliable without calibration, aggregation, or human review. This centered screenshot shows a computer screen. Take a moment to scan the overall layout. Notice window arrangement, toolbars, or menus at the top, and any status indicators or side panels. These elements reveal how the application organizes information and where you should look first. This figure illustrates that a single prompt can yield multiple distinct responses from the same model. We'll use this section to explore sources of that variability and why it matters for testing and reliability. People expect consistency in conversation. If someone called you a different name each time, it would feel jarring. The same is true for AI. Inconsistent responses break trust and make interactions harder to use, so aim for predictable behavior. There are 3 practical ways to make model outputs consistent for the same input. First, cache the response, so repeated requests return the identical answer. Second, lock sampling parameters like temperature, top P, and top K to reduce randomness. And third, set a fixed seed so the random number generator produces the same token choices each run. Even if you fix seeds, code, and inputs, different machines can still produce different outputs. They execute instructions and represent numbers in slightly different ways. Hosting your own model gives you control over the hardware. Using a third-party API hands that control to the provider who may introduce variability. Tuning output settings to produce consistent results helps, but it won't build confidence if that consistency only appears in one context. Imagine a teacher who grades reliably in one room but gives wildly different scores in another. You'd doubt their fairness. Aim for systems that stay stable across different contexts, not just a single setup. Even slight changes to an input can lead a model to produce very different outputs. Adjusting generation settings like temperature or max tokens is good practice, but it won't make different inputs yield the same response. For closer control, you need careful prompt engineering and a memory system, which are discussed in later chapters. In AI, a hallucination is when a model confidently produces information that is false or fabricated. In this section, we'll look at common causes and practical ways to detect and reduce these errors. When a model invents facts, it can invalidate any task that depends on accuracy. For instance, you wouldn't want pseudoscientific claims when explaining vaccine pros and cons. And in June 2023, a law firm was fined after submitting fictitious legal research generated by ChatGPT. The tendency for generative models to produce incorrect or fabricated content, what we now call hallucination, was observed well before transformers, and the term foundation model became common. Papers dating back to 2016 documented this behavior in text generation, and the community has worked on detecting and measuring hallucinations in NLG ever since. Methods for evaluation are discussed in Chapter 4. Random sampling picks among outputs the model already considers probable, but that doesn't answer how a never-seen idea becomes probable. A model can assemble novel combinations or abstractions that we can't trace back through the training data, and because we can't exhaustively verify the dataset, we can't be certain whether an idea was learned or invented. This capacity to build things beyond our understanding is both powerful and risky. You can't eliminate hallucinations until you understand their cause. Broadly, researchers propose 2 hypotheses. One blames the training signal and data, noise, gaps, or objective mismatch, and the other blames the model's probabilistic next token prediction and decoding, which can produce plausible but ungrounded statements. We'll unpack each hypothesis in the next sections. Ortega et al., DeepMind, 2021, suggested one common cause of hallucinations. The model doesn't reliably distinguish the data it was trained on from the tokens it generates. As a result, it can treat its own outputs like ground truth and either repeat errors or fabricate plausible-sounding facts. If a model generates, Chip Win is an architect, that generated sentence becomes part of the context for the next token. The model treats its own output like a given fact, so a small error can be amplified into many more false claims, a process Ortega and colleagues call self-delusion, a root cause of hallucinations. Here, LLMs V1.5-7b inspects a shampoo bottle but convinces itself the product is milk. It then incorrectly adds milk to the extracted ingredient list, an example of visual grounding failure and self-delusion, a kind of hallucination. Look closely at the label. This bottle shows preparation and storage instructions, measurement markings, and small safety icons. Notice how layout, Icons and concise text work together to communicate safe handling and use at a glance. This figure presents a clear example where LLMs v1.5-7b confidently asserts incorrect information from an image, a form of self-delusion. We'll use this example to highlight how multimodal models can produce plausible but false claims and what to watch for when diagnosing them. Zhang et al., 2023, label this effect snowballing hallucinations. After making an incorrect assumption, a model often invents further facts or reasoning to support that first mistake. This cascade can cause it to fail on questions it would otherwise answer correctly. See Figure 225 for concrete examples. This is a screenshot of a computer application window. In this section, we'll see how a single wrong premise can steer the model's reasoning. Even if the model knows that 9,677 isn't divisible by 13, an early incorrect assumption can make it assert the opposite, showing how errors propagate. DeepMind showed two complementary fixes. The first borrows from reinforcement learning. Train the model to distinguish user prompts, observations, from its own generated tokens, actions, which helps prevent it from treating its guesses as facts. The second is supervised. Include explicit factual labels and counterfactual examples in training, so the model learns when an answer would be incorrect. This hypothesis says hallucinations can arise when models are trained to mimic labeler answers that rely on knowledge the model itself doesn't have. During supervised fine-tuning, the model copies labeler's wording and can therefore assert facts it cannot verify. In principle, we could ask labelers to attach their sources or background knowledge, but recording every tacit source and scaling those annotations is impractical. John Schulman suggested that LLMs can tell when they truly know something, and that insight could let us prevent hallucinations by forcing models to answer only from verifiable knowledge. He proposed two approaches: verification, asking the model to retrieve or cite the sources behind each answer, and reinforcement learning, where the reward model, trained from pairwise comparisons, is shaped to punish made-up facts more strongly. OpenAI later reported RLHF can reduce hallucinations, but the InstructGPT paper actually shows RLHF increased hallucination rates in their evaluation. See their Figure 226. Still, RLHF improved other response qualities, and human labelers prefer the RLHF model over the SFT-only model, illustrating a trade-off between different kinds of errors and overall usefulness. This screenshot shows the application's main user interface. Notice the central content area, the surrounding menus or toolbars, and any highlighted text or icons. These tell you where to read output, enter input, and access controls. When studying screenshots like this, first map the major regions, content, navigation, status, so you understand how the workflow is organized. This figure compares the same base model after supervised fine-tuning, SFT, and after additional RLHF tuning, known as InstructGPT. It shows that adding RLHF increased hallucination in this study. Ouyang et al., 2022, which we'll examine next. If we treat a foundation model as only knowing what it knows, you can cut hallucinations by explicitly asking for truthful answers and by having the model admit uncertainty. Short, concise replies also help because fewer generated tokens reduce the chance of invented facts. Chapters 5 and 6 cover practical prompting and context construction techniques that further mitigate hallucination. These two ideas complement each other. The self-delusion hypothesis explains how self-supervision can make a model generate consistent but false content, while the mismatched internal knowledge hypothesis explains how external supervision can push the model toward incorrect internal representations. Both mechanisms can act together to produce hallucinations. Telling when a model is inventing facts is difficult. Much like spotting when a person is lying or making things up. We can't yet eliminate hallucinations, but Chapter 4 surveys methods to detect and measure them, so we can avoid serving clearly hallucinated answers to users. This section recaps the main concepts and key takeaways from the lesson. I'll highlight the most important results you should remember and any remaining questions to consider. This chapter covered the main design trade-offs you face when building or choosing a foundation model. I purposely avoided low-level training mechanics and instead focused on practical factors that help you decide which pre-built model to use and how to apply it effectively. A model's abilities come from the examples it sees during training. Large models are often built from whatever data is available, so they do well on common tasks but can miss niche languages or domains. Targeted curation of training data, especially for low-resource languages, is therefore often necessary. After collecting data, the next step is architecting the model, choosing its structure and size before training. Those choices determine capability, compute needs, and common failure modes. The transformer is the dominant architecture for language foundation models. We examined why it works well and where it falls short. We measure a model's scale by three numbers: the number of parameters, the number of training tokens, and the flops needed to train. Both model size and data size determine how much compute we need, and the scaling law tells us the optimal split of parameters versus tokens for a given compute budget. Right now, larger models usually improve performance, but scaling bottlenecks raise the question of how long that trend will continue. Pre-training with noisy or self-supervised data often yields outputs that don't match what users want. We address this with post-training in two steps: supervised fine-tuning to teach correct behavior, then preference fine-tuning to align outputs with human judgments. But because human preferences are diverse and hard to capture mathematically, these methods remain imperfect. Sampling is the process a model uses to pick each next token, which makes its outputs inherently probabilistic. That randomness is why models can be creative and engaging, but it also causes variability between runs and can produce mistakes or hallucinations. AI models are inherently probabilistic, so workflows must account for uncertainty and variability rather than assuming deterministic behavior. The goal of the next sections is to make AI engineering systematic. The immediate, practical step is to build a robust evaluation pipeline that detects failures and unexpected changes. Evaluation is so central for foundation models that it gets 2 chapters starting next. Yeni Jun's study shows GPT-4 can solve many math problems, but its accuracy falls off for some languages. A key cause is how inputs get tokenized and represented to the model. You can reproduce and inspect this effect using OpenAI's tokenizer to see how prompts are split into tokens and how that may change model behavior. Model behavior often reflects the data it was trained and aligned on. If pre-training or alignment data sets underrepresent Chinese language material or China-focused narratives, the model will learn fewer patterns about those topics and can appear biased or less informed. This Washington Post article reveals a curated set of websites that AI systems draw on to shape their style and answers. Understanding those sources helps explain why models like ChatGPT can sound confident, but also inherit specific perspectives, gaps, or mistakes. For text, you can often apply domain keywords as quick heuristics, but images lack similarly reliable shortcuts. Most analyses of vision datasets focus on low-level properties, image size, resolution, or video length, rather than semantic content. That gap makes curating and filtering image datasets harder than for text. 5ML fundamentals tied to model training are intentionally left outside this book's core scope, but I still introduce specific ideas when they matter. For example, Chapter 1 covers self-supervision, how models create their own labels, and Chapter 7 explains backpropagation, how training errors update model parameters. RNNs reuse the same weights over many time steps, so gradients get multiplied repeatedly as they propagate backward. If those multipliers are less than 1, the gradients shrink toward 0, vanishing, and the model can't learn long-range dependencies. If greater than 1, they grow exponentially, exploding, causing unstable training. This paper introduced the neural attention mechanism for sequence-to-sequence translation. Rather than compressing the source into one fixed vector, The decoder learns soft alignment weights and attends to relevant source positions, which greatly improves handling of long or complex sentences. Because tokens are processed in batches, inputs are stored as a 3D tensor with shape n, batch size, times t, sequence length, times 4096 vector size. Each token produces k, q, and v vectors of length 4096. So the full k, q, and v tensors also have shape n times t times 4096. Researchers tried many fancy activation functions, but large models like LLMs rarely gain from them. The key requirement is a nonlinearity to break the feed-forward layer's linearity. Simpler activations are faster and save training compute and memory, so they're usually preferred. Fun fact: Ilya Sutskever is a co-founder of OpenAI and an influential early researcher. He was first author on the Seq2-Seq paper that shaped modern sequence models and second author on AlexNet, the breakthrough deep convolutional network, a sign of his broad impact across subfields. Ilya Sutskever's point is that neural networks can emulate many computer programs, and gradient descent is essentially a search through those emulated programs to find the one that best solves a task. Because existing architectures can already simulate a wide range of programs, a new architecture will only outperform them if it can simulate programs the old ones cannot. For a deeper dive, see Sutskever's Simons Institute Talk, 2023. The original transformer was developed at Google with TPUs as the primary target, so its early implementations and performance expectations assumed TPU hardware. Later, engineers adapted and optimized those implementations for GPUs, changing memory layouts and parallelism strategies so the model would run efficiently on more common GPU hardware. The memory figures we've mentioned are optimistic. In practice, you need more memory because of optimizer states, activations, and runtime overhead. Chapter 7 walks through how to compute a model's total memory usage step by step. This is a practical conversion. A 50,000-word book corresponds to roughly 67,000 model tokens, or about 1.34 tokens per word. Use this estimate when planning context window requirements or estimating token-based costs for language models. When training at massive scale, teams typically make just a single pass over the data, one epoch. The datasets are huge and compute costly, so one epoch already exposes the model to enormous token variety. This shapes convergence behavior and decisions about data curation and augmentation. The reported 16-flop/S uses FP32 single precision arithmetic. Chapter 7 covers floating point formats. Precision affects numerical results and performance, so always check which format a flop/S number refers to before comparing. Right now, you can rent NVIDIA H100 instances from cloud providers for roughly $2 to $5 per hour. Hardware and cloud pricing are dropping fast, so expect these hourly rates to fall further and to vary by provider, region, and contract type. Researcher Jaska Soldickstein published a clear visualization that highlights which hyperparameter settings tend to work and which tend to fail. It's a compact, practical guide you can consult when tuning models. Follow the X post for the full chart and examples. Anthropixiodorio Amade claimed that under the scaling hypothesis, the idea that larger models trained with more compute get predictably better, a single $100 billion model might reach the problem-solving level of a Nobel laureate. It's a provocative forecast that hinges entirely on the hypothesis continuing to hold across real-world scientific and intellectual tasks. AI can both create an article and, with a click, translate it into many languages. Thompson et al., 2024, show this multiplies AI-produced material across the web, which can amplify low-quality or duplicated content in multiple languages. A useful analogy is that a pre-trained model speaks like a web page. It assembles text from stored patterns and templates rather than expressing intentions. That's why outputs can read as fluent and informative but still lack beliefs, goals, or grounded understanding the way a human reply would. We won't cover reinforcement learning fundamentals here, but one key point is practical. RL enables direct optimization for complex, hard-to-specify goals. For example, you can train policies using reward signals derived from humans, so the model learns behaviors aligned with human preference. Sometimes we deliberately build models that are misaligned with safe goals in order to test threats. For example, training a model to generate highly convincing fake news lets researchers measure how believable AI misinformation can be and informs defenses, detection tools, and policy choices. A helpful mental picture is that increasing sampling temperature flattens the model's probability distribution. That makes generation more random. Lower probability tokens get a bigger chance to appear, useful as a heuristic, though not a formal definition. The argmax of a function returns the input value where the function attains its largest output. We write it as argmax f x, which yields the x, or set of x's, that maximize f. If several inputs tie, the argmax can be multiple points. Underflow occurs when a number is smaller than the smallest positive value a format can represent, so the system effectively rounds it down to 0. This loses information, precision, and can break calculations that rely on very small non-zero values, for example, in iterative algorithms or probability computations. OpenAI's API currently returns log probabilities only for the up to 20 most likely tokens. It used to let you request log probs for arbitrary text, but that capability was removed in September 2023. Anthropic does not expose model log probs, so you can't retrieve token-level probabilities from their models. Many paid model APIs build based on the number of output tokens, that is, how much text the model returns. Longer responses therefore cost more, so when you integrate an API, you should set sensible token limits or truncate outputs to control expenses. When you need several outputs from the same input, avoid redoing the expensive input work each time. Preprocess or encode the input once, for example, tokenize or compute embeddings, and reuse that result for every output to save time and cost. The OpenAI API accepts a best underscore of parameter, so the model can generate multiple completions and return the single completion with the highest average log probability. For example, best underscore of equals 10 asks for 10 candidates and selects the most likely one. Wang et al. Named this technique self-consistency. It involves sampling multiple independent reasoning traces or answers from a model and then aggregating them, commonly by majority vote, to produce a more reliable final prediction. When a model is brittle, regularly failing, or fragile, you're usually better off replacing it than endlessly patching it. That replacement can be a different architecture, retraining with better data, or an ensemble. Always validate the new model for accuracy and safety before putting it into production. In practice, the share of correctly generated JSON can run from nearly 0% up to the high 90s, depending on the model and the task. Because of that variability, you should always build validation and error handling into any pipeline that relies on model-generated JSON. You can train a model from scratch if your data follows the right format, but this book doesn't teach how to build models from the ground up. We'll focus instead on using, adapting, and fine-tuning existing models to solve problems. Many fine-tuning tools will attach a classifier head so the model outputs labels directly, saving extra implementation work. OpenAI used to offer this as part of its fine-tuning flow, but that capability is disabled now, so you may need to add the head yourself or use a different workflow. Even when odds are tiny, an outcome can still occur. That matters for risk assessment. We shouldn't ignore rare possibilities just because they're unlikely. I reviewed 3 months of customer support for an AI client and found about 1/5 of questions were about how to handle inconsistent model outputs. In a July 2023 panel with Drew Houston and Harrison Chase, we agreed that hallucination, models inventing facts, is the single biggest blocker for many enterprise AI use cases because it breaks trust.